Hello there and welcome to Science for Sleep, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we're setting our sights on some of the most overlooked worlds in the universe. Not planets, not stars, not black holes or distant galaxies. Instead, we're spending the evening with their quieter companions, the objects that spend billions of years circling larger worlds, rarely demanding attention, yet often turning out to be far more interesting than anyone expected. Moons. At first glance, a moon might seem simple. After all, most of us grow up with just one. The moon hangs overhead so often that it's easy to treat it like part of the scenery. It's there during evening walks, peeking through clouds, following long drives home, and occasionally appearing in photographs when someone points at it and says, "Look how huge it is tonight." Yet the moment we begin exploring the rest of the solar system, something surprising happens. Moons stop being familiar. Instead, they become strange. Some are covered in volcanoes that erupt continuously. Others hide oceans beneath shells of ice. Some have thick atmospheres, rivers, lakes, weather systems, and clouds. A few are so large they would easily qualify as planets if they orbited the sun directly. Others are tiny captured wanderers that look more like cosmic leftovers than proper worlds. And beyond our solar system, there may be moons orbiting planets around distant stars. There could even be moons drifting through interstellar space entirely alone, separated from any planet they once called home. For objects that usually get labelled as sidekicks, moons have a remarkable talent for stealing the spotlight. Before we begin though, I'd love to know something. Where are you listening from tonight? And if you happen to glance outside a window, can you see the moon from where you are? Perhaps it's shining brightly overhead. Perhaps it's hidden behind clouds. Maybe it's below the horizon entirely, waiting for its turn later tonight. Whatever the answer, it's worth remembering that nearly every human who has ever lived has looked at that same object and wondered about it. Farmers watched it to track the months. Sailors used it to navigate. Poets wrote about it. Scientists measured it. Children pointed at it. And more than a few people have spent sleepless nights staring at it when they probably should have been doing something else. If you find this little journey relaxing, interesting, or simply a pleasant way to wind down at the end of the day, I'd be grateful if you gave the video a like and maybe subscribed as well. It helps this quiet corner of science reach other curious listeners who might enjoy falling asleep while thinking about the universe. Now get comfortable, settle into your favourite position, let your thoughts slow down a little, and let's begin. Because once you start looking closely at moons, it becomes surprisingly difficult to stop. The story begins with a simple question. What exactly is a moon? At first, the answer seems obvious. A moon is an object that orbits a planet. Simple enough. Except nature, as usual, has little interest in keeping things simple. Take our own moon. It's enormous compared to Earth. In fact, if you compare a planet to its moon, few pairs in the solar system are quite as evenly matched. Earth's moon is more than 1/4 the diameter of Earth itself. That may not sound particularly impressive until you realise most moons are tiny compared to the worlds they orbit. Jupiter's giant moon Ganymede, for example, is absolutely enormous by moon standards, yet Jupiter is so huge that Ganymede still appears relatively small beside it. Earth and the moon are different. In some ways, they're more like partners than a typical planet-moon pair. Then there are worlds like Pluto and Charon. Some astronomers argue that neither should truly be considered dominant over the other. Instead, they behave more like a double system, with both objects orbiting a point in space located between them. Already, our neat definition of a moon is beginning to wobble, and we've barely left home. Travel outward to Jupiter and things become even stranger. Jupiter currently has dozens upon dozens of known moons. Some are massive worlds, others are little more than captured rocks. A few likely formed alongside Jupiter itself billions of years ago. Others appear to have arrived much later, becoming trapped by Jupiter's immense gravity after wandering too close. Saturn offers an even larger collection. Its moon count is so high that astronomers occasionally seem to discover new members every time they take a careful look. Some are icy, some are oddly shaped. Some help maintain Saturn's rings. Some may contain hidden oceans. One even possesses lakes and rivers, not of water, of liquid methane. Imagine standing beside a shoreline beneath an orange sky where rain falls from hydrocarbon clouds. That world exists, and it's a moon. Meanwhile, Neptune has Triton, a moon that likely began life elsewhere before being captured. It travels around Neptune in the opposite direction from most major moons. That's often a clue that something unusual happened long ago. It's as if Triton arrived late to the party and never quite followed the house rules. The more astronomers studied moons, the more they realized these objects weren't simply smaller versions of planets. They represented an astonishing variety of worlds. In many cases, they turned out to be more active and interesting than the planets they orbit. That realization arrived dramatically in 1979. The spacecraft Voyager 1 swept past Jupiter and sent back images of its moons. Scientists expected cold, ancient, crater-covered surfaces. Instead, they found Io. Io looked alive. Not literally alive, of course, but geologically alive. Volcanoes erupted across its surface. Plumes shot hundreds of kilometers into space. Entire landscapes appeared to be continuously renewed. At the time, it was the most volcanically active world ever observed. Not Earth, not Venus, a moon. Then came Europa. Beneath its cracked icy shell, scientists suspected something extraordinary. An ocean. A vast ocean hidden beneath frozen crust. An ocean containing more water than all of Earth's oceans combined. For decades, that possibility has fascinated researchers, because wherever liquid water exists, one question inevitably follows. Could life exist there too? Notice how quickly the conversation changed. We began with moons. We ended up discussing alien oceans and possible extraterrestrial life. That's the effect moons tend to have. They lure you in with familiarity, and then quietly reveal something astonishing. Even our own moon still holds surprises. For centuries, people imagined it as a barren world. A dusty sphere covered with craters and little else. Then came spacecraft, landers, orbiters, and increasingly sophisticated instruments. Scientists found evidence of water ice in permanently shadowed craters near the poles. Tiny traces perhaps left by comets, asteroids, or ancient geological processes. Today, those frozen deposits are considered valuable enough that future explorers may one day use them to produce drinking water, breathable oxygen, or even rocket fuel. Suddenly, the moon transformed from a destination into a resource, a stepping stone, a place humanity may return to again and again. Of course, humans have always had a special relationship with moons. Long before telescopes existed, the moon served as a natural calendar. Many ancient cultures based their months on lunar cycles. In fact, the word month itself is deeply connected to the moon. Watch the moon carefully over several weeks, and you'll see its appearance change. New moon, crescent, quarter, gibbous, full. Then the cycle repeats. Reliable, predictable, comforting. Ancient civilizations noticed this pattern thousands of years before anyone understood gravity or orbital mechanics. They built calendars around it, scheduled festivals around it, organized agriculture around it. The moon became one of humanity's earliest clocks, and perhaps that's part of the reason we feel connected to it. It isn't just another object in the sky. It's been accompanying us for our entire history. Every civilization knew it. Every generation inherited it. Every child eventually looks up and asks questions about it. Questions that often begin simply. Why does it change shape? Why does it follow us? How far away is it? And eventually, why is it there at all? That last question turns out to be particularly important, because not every planet has a moon. Mercury doesn't. Venus doesn't. Some worlds collect entire families of moons. Others travel alone. Why? The answer depends on how moons form. And a scientist gradually discovered there isn't just one way. Some moons are born alongside their planets. Others emerge from gigantic impacts. Some are captured. Some may even be assembled from debris rings. Nature appears perfectly happy using multiple methods to create them. It's a bit like asking how towns form. Some grow around rivers, some around trade routes, some around mines, others around ports. Different beginnings can produce remarkably different places. Moons are much the same. Their origins shape their futures. A moon born beside a giant planet may spend billions of years in a stable orbit. A captured moon may arrive with a tilted path and a chaotic history. A moon created by collision may inherit characteristics unlike anything else nearby. Every moon carries clues about its past, and by reading those clues, astronomers learn not only about the moon itself, but about the history of entire planetary systems. In a sense, moons are cosmic historians. They preserve evidence of ancient events that occurred billions of years ago: massive collisions, planetary migrations, gravitational encounters. The solar system we see today wasn't always arranged this way. The giant planets likely moved, objects were scattered, worlds collided, entire populations of moons may have been destroyed, replaced, or captured. The survivors tell the story. That's one reason scientists love studying them. Another reason is much simpler. Moons are everywhere. Once astronomers began searching carefully, they discovered that moons are not rare accessories. They are common outcomes of planetary formation. And if planets are common throughout the galaxy, then moons may be even more common than we imagine. At this very moment, there may be trillions upon trillions of moons orbiting worlds scattered across the Milky Way. Some larger than Earth, some smaller than cities, some frozen solid, some covered by oceans, some illuminated by giant planets looming overhead. Some existing in systems utterly unlike anything we've ever seen. Most of them will never appear through a telescope in your backyard. Many remain invisible even to our most powerful observatories, yet they're there, quietly circling their parent worlds, following paths established millions or billions of years ago. And among that immense population are examples so strange that if someone described them in a science fiction novel, they might seem exaggerated. Fortunately for science writers everywhere, reality continues to outperform imagination. Because over the course of this journey, we're going to encounter moons with volcanoes, moons with weather, moons trapped by gravity, moons that help shape rings, moons hiding oceans, moons larger than planets, and moons that may wander between the stars. The remarkable thing is that every one of those categories exists because the universe keeps finding new ways to build worlds. And before we can explore those different kinds of moons, it helps to understand the basic question sitting underneath all of them. Why do moons exist in the first place? One of the easiest assumptions to make about moons is that they're somehow secondary. We tend to think of planets as the main characters and moons as supporting cast members, little companions tagging along for the ride. But if we could travel back to the beginning of the solar system, long before Earth had oceans or Saturn had rings, we'd discover something surprising. Moons are not accidents, at least not usually. They're often a natural consequence of the same processes that create planets themselves. To understand why moons exist at all, we need to return to a time more than 4.5 billion years ago, when the solar system was not a collection of neatly organised planets orbiting the Sun. Instead, it was a vast spinning cloud of gas and dust. There were no continents, no moons, no rings, and certainly no astronomers arguing over definitions. There was only raw material. Imagine an enormous disk stretching billions of kilometres across. At its centre, the young sun was forming. Around it, countless particles of ice, rock, and dust were constantly colliding. Most collisions were gentle, some were violent. Tiny grains stuck together and became pebbles. Pebbles became larger clumps. Those clumps became planetesimals, the building blocks of planets. Over millions of years, gravity took over. Larger objects attracted more material, growing bigger and bigger. Eventually, worlds emerged. Mercury, Venus, Earth, Mars, the giant planets. And, as it turns out, the conditions that created planets often created moons too. One reason is remarkably simple. Gravity rarely likes to work alone. Whenever a large object forms, smaller objects often end up caught in its influence. You can see this principle throughout nature. Around stars, planets gather. Around planets, moons gather. Around moons, tiny particles may even gather to form temporary rings or clouds. Gravity creates relationships. The bigger an object becomes, the stronger its ability to hold companions nearby. This means that as giant planets formed in the outer solar system, they didn't merely collect material for themselves, they also created miniature versions of the solar system around them. Jupiter is perhaps the best example. Today, Jupiter possesses a staggering collection of moons. Some are tiny irregular rocks only a few kilometers across. Others are enormous worlds in their own right. Ganymede, for instance, is larger than the planet Mercury. If Ganymede orbited the Sun directly instead of Jupiter, many people would probably call it a planet without hesitation. Yet it remains classified as a moon simply because of what it orbits. During Jupiter's formation, a disk of gas and dust surrounded the growing giant planet. This smaller disk functioned much like the larger disk around the young Sun. Within that environment, moons began forming. Tiny particles collided, objects grew, gravity pulled material together, and eventually several major moons emerged. In a sense, Jupiter created its own miniature planetary system. Saturn likely experienced something similar. So did Uranus. So did Neptune. Some moons were born alongside their planets from the very beginning. They didn't arrive later. They grew up together. If planets were families, these moons would be siblings rather than adopted members. Scientists call these regular moons because their orbits tend to be orderly. They travel in the same direction their planet rotates. They remain relatively close. Their paths are usually nearly circular. Everything about their motion suggests they formed from the same rotating disk of material. But formation alongside a planet is only one way to create a moon. Nature, as always, prefers variety. Let's return briefly to Earth. Our moon is unusual, not because it's beautiful, though many people would certainly argue that point. Not because it's close, not because it causes tides. It's unusual because evidence suggests it formed in a completely different way. The leading explanation is called the giant impact hypothesis. According to this idea, the young Earth experienced a truly catastrophic collision early in its history. A Mars-sized object, often called Theia, slammed into our planet. This wasn't a gentle bump. It was an impact so enormous that parts of both worlds were blasted into space. Rock vaporized, material melted, debris spread into orbit around Earth. For a time, our planet may have been surrounded by a glowing ring of molten rock. That ring didn't remain a ring forever. Gravity went to work, pieces collided, fragments merged. Gradually a single larger object emerged. The Moon. If this theory is correct, Earth's companion wasn't born beside our planet in the same way Jupiter's large moons formed. Instead, it was created from the aftermath of a planetary disaster, which means every time we look at the Moon, we're seeing the product of one of the most violent events in Earth's history. It's remarkable to think about. Something that feels permanent and familiar may have originated from chaos on a nearly unimaginable scale. The giant impact hypothesis also explains why the Moon and Earth share many similarities in composition. The material that created the Moon likely came directly from Earth itself, mixed with debris from the impactor. In a very literal sense, parts of Earth became the Moon. And parts of the Moon were once part of Earth. That relationship makes our system different from many others. The Moon is not merely accompanying Earth, it's deeply connected to Earth's origin story. Without that collision, our world might look very different today. Earth's rotation would be different, its tides would be different, its long-term climate stability might even be different. In ways we're still studying, the Moon helped shape the environment in which life eventually emerged. Not bad for an object sometimes dismissed as a giant rock. Of course, there is another method by which moons can appear, and this one feels a little like cosmic kidnapping. Imagine a small world travelling through space. Perhaps it's an asteroid. Perhaps it's a dwarf planet. Perhaps it's a moon orbiting something else. Whatever the case, it passes too close to a giant planet. Normally the object would simply continue on its journey, but occasionally circumstances align perfectly. Energy gets redistributed, gravitational interactions occur, and the wandering object becomes trapped. Instead of escaping back into space, it remains in orbit. A captured moon is born. Neptune's largest moon, Triton, is one of the strongest candidates for this process. Triton behaves differently from many major moons. It travels around Neptune in a retrograde orbit. That means it moves opposite the planet's rotation. This is unusual. If Triton formed alongside Neptune, astronomers would expect its motion to match the planet's rotational direction. Instead, its orbit suggests an outsider arrived later and got caught. Evidence indicates Triton may once have been an independent object in the distant outer solar system. Perhaps it belonged to a binary pair. Perhaps it wandered freely. Whatever its origin, Neptune eventually claimed it. Captured moons are fascinating because they're immigrants. They bring stories from elsewhere. Their compositions may differ from neighbouring moons. Their orbits may be tilted, elongated or unstable. They often carry clues about regions of the solar system far beyond their current homes. Some of the strangest moons known today likely fall into this category. And yet even these aren't the end of the story. There is still another possibility. Sometimes moons may emerge from rings. This process is particularly intriguing because it means a planet's rings and moons can be closely related. Picture countless particles orbiting a planet. Some collide, some merge. Given enough time, larger objects may begin forming within the ring system. If conditions allow, those growing objects can eventually become moons. Likewise, moons can sometimes break apart and contribute material to rings. The relationship works both ways. It's less like separate categories and more like a continuous cycle. Material moves, gravity reshapes it, new structures emerge. Saturn provides some of the best examples of these interactions. Its rings and small moons appear linked in ways scientists are still trying to fully understand. In some cases, moons may have formed from ring material. In others, ring material may have originated from shattered moons. The line between the two isn't always clear. What's becoming obvious is that moon formation isn't a single recipe. It's more like a collection of recipes. Some moons form beside planets, some form from collisions, some are captured, some grow from rings. Different histories produce different worlds, and those histories matter. A moon's origin influences nearly everything that follows: its size, its orbit, its geology, its internal structure, even its chances of hosting liquid water. Take Io and Europa, both orbit Jupiter, both likely formed from the same circumplanetary disk. Yet tidal forces affected them differently. One became the most volcanic world in the solar system. The other developed a hidden ocean. Their shared beginning did not guarantee identical futures. The same is true throughout the universe. Two moons can start similarly and end up dramatically different. In fact, one of the most important lessons astronomy keeps teaching us is that nature enjoys experimentation. Give gravity enough material and enough time, and it will produce astonishing variety. That's partly because gravity itself is deceptively simple. Every object attracts every other object. That's the basic rule. Yet from that simple rule emerge stars, planets, rings, galaxies and moons. Countless moons, perhaps more moons than planets. Think about that for a moment. When people imagine the universe, they often picture planets, rocky worlds, gas giants, Earth-like environments. But statistically speaking, moons may be among the most common types of worlds in existence. Every giant planet can host dozens, some host hundreds. Across billions of planetary systems, the total number becomes almost impossible to comprehend. Many of those moons may never be visited. Many may never even be directly observed. Yet they exist, silent companions orbiting larger worlds throughout the galaxy. Some may possess oceans, some may possess atmospheres, some may even provide conditions suitable for life. For generations, scientists focused primarily on planets when searching for potentially habitable environments. Today, that perspective is expanding, because moons can be interesting places too, perhaps extraordinarily interesting. After all, if Europa contains an ocean beneath its ice, and Enceladus contains an ocean beneath its ice, then hidden seas may not be unusual. They may be common. And if hidden oceans are common, entirely new possibilities emerge. Suddenly, moons stop being supporting characters. They become destinations, they become laboratories, they become worlds worthy of study in their own right. That shift in perspective happened gradually. The more spacecraft visited the outer solar system, the harder it became to ignore the evidence. Moons weren't simply decorative accessories attached to planets. Many were active, evolving places with unique histories. Each had its own story, its own geology, its own environment, its own surprises. And perhaps that's the most important answer to our original question. Why do moons exist at all? Because the same forces that build the universe naturally create them. Gravity gathers material. Material forms worlds. Worlds gather companions. The process repeats over and over again. Not because the universe intends to create moons, but because moons are often the inevitable result of how planets and gravity behave. They're a natural outcome of cosmic construction, and once they form, they begin following their own paths. Far beyond the familiar sight of Earth's moon hanging over quiet landscapes and city skylines, an entire population of moons circles the giant planets of our solar system. Some are icy, some are rocky, some hide oceans, some erupt with volcanoes. Yet despite their differences, many of them belong to the same broad family. These are the regular moons. The name sounds almost disappointingly ordinary, as though astronomers ran out of creativity halfway through the classification process. But the term has a very specific meaning. A regular moon is one that formed alongside its parent planet during the early days of the solar system. Rather than arriving later as captured wanderers, these moons grew from the same rotating disk of gas, dust, ice, and debris that surrounded a young planet while it was still forming. In a sense, they grew up together. If planets have childhood friends, these moons would be them. They've spent billions of years travelling together, orbit after orbit, through changing ages of the solar system. And although they share similar origins, what happened afterward transformed them into remarkably different worlds. Perhaps the easiest place to begin is with the only moon humans have ever visited, our moon. For all the attention given to distant moons around giant planets, Earth's moon remains one of the most extraordinary objects we know. Part of that comes from familiarity. The moon feels close, not merely in distance, but emotionally. Human beings have lived beneath its changing phases for thousands of generations. Entire calendars were built around it. Stories emerged around it. Religions referenced it. Poets filled pages with it. Meanwhile, scientists spent centuries trying to understand it. Yet despite this long relationship, the moon continues to surprise us. Its surface preserves a record of ancient impacts stretching back billions of years. Vast dark plains known as Maria were formed when enormous impacts opened pathways for lava to flood across the surface. The brighter highlands are even older. Some regions date back to the earliest history of the solar system. Walking across the moon would be like walking through a museum of planetary history. Every crater tells a story. Every layer preserves evidence of events that occurred long before life appeared on Earth. Interestingly, the moon's existence may have helped make Earth a more stable place. Its gravity influences our tides. It also helps stabilize Earth's axial tilt. Without the moon, our planet's climate might have experienced far more dramatic long-term changes. Life could still have emerged, or perhaps not. Scientists continue debating exactly how important the moon has been. What is clear is that Earth and the moon have influenced each other for billions of years. They are partners in a cosmic dance that continues even now. In fact, the moon is slowly drifting away, not quickly enough to notice during a human lifetime, of course. The separation occurs at roughly the speed your fingernails grow, which means that every year the moon moves slightly farther from Earth. It's a reminder that even seemingly permanent systems continue evolving. Now let's leave Earth behind and travel outward to Jupiter. Here we encounter one of the most remarkable collections of moons in the solar system. The 4 largest are known as the Galilean moons, because they were discovered by the astronomer Galileo Galilei in 1610. That discovery changed history. Before Galileo pointed his telescope toward Jupiter, many people believed everything in the heavens revolved around Earth. Then he observed 4 small objects moving around Jupiter. Clearly not everything orbited our planet. The universe suddenly became much larger and far more interesting. The first of these great moons is Io. At first glance, Io looks almost unreal. Its surface is covered in yellows, oranges, reds, blacks and whites. Rather than appearing like a typical crater-covered moon, it resembles an artist's palette after a particularly enthusiastic afternoon. The reason is simple. Io is constantly resurfacing itself. It is the most volcanically active world known. Not the most volcanically active moon, the most volcanically active world, period. Hundreds of volcanoes operate across its surface. Some erupt lava fountains reaching extraordinary heights. Others produce enormous plumes that rise far above the moon itself. Standing on Io would be impossible for numerous reasons, but if it were somehow safe, the landscape would feel alive. Not biologically alive, geologically alive. The surface changes continuously. New lava flows emerge. Sulfur compounds settle across the terrain. Ancient features disappear beneath fresh deposits. What powers all of this activity? Jupiter, or more specifically gravity. As Io orbits Jupiter, enormous tidal forces squeeze and stretch the moon. The process generates heat inside its interior. Imagine repeatedly bending a paperclip until it becomes warm. Now scale that concept up to the size of an entire moon. The result is Io, a world where gravity itself acts like a planetary furnace. Not far away orbits Europa. And Europa may be even more fascinating. At first, Europa appears calm. Its bright icy surface reflects sunlight beautifully. Long cracks and streaks spread across the landscape like fractures in frozen glass. Compared to Io's volcanic chaos, Europa seems peaceful. Yet appearances can be deceiving. Beneath that frozen crust likely lies a global ocean. Not a small ocean, not a regional sea. A global ocean, one that may contain more water than all of Earth's oceans combined. The possibility has captivated scientists for decades. Liquid water, energy sources, chemical ingredients. These are some of the fundamental requirements associated with life as we know it. Europa appears to possess all 3. No one knows whether life exists there, at least not yet. But among the many worlds of the solar system, Europa consistently ranks near the top of the list of places where scientists hope to find evidence of biology beyond Earth. It's remarkable to think that one of the most promising environments for life may exist beneath kilometers of ice, on a moon orbiting a giant planet hundreds of millions of kilometers away. Continue outward and we reach Ganymede. If moons held competitions for size, Ganymede would win. It is the largest moon in the solar system, larger than Mercury, larger than Pluto, larger than many objects people casually think of as planets. Yet Ganymede remains a moon because of what it orbits. Its size alone would make it noteworthy. But Ganymede has additional distinctions. It possesses its own magnetic field. That's extremely unusual. Among moons, it stands almost alone in this regard. A magnetic field suggests internal complexity. It hints at processes occurring deep beneath the surface. Scientists believe Ganymede may also contain subsurface oceans layered beneath ice. In fact, some models suggest multiple layers of ice and water stacked atop one another. Rather than a single ocean, there may be several. If true, the interior of Ganymede could be far more complicated than anyone imagined when it was first discovered through a telescope centuries ago. Then comes Callisto. At first glance, Callisto seems quieter than its siblings. Io erupts, Europa hides an ocean, Ganymede generates a magnetic field. Callisto simply sits there. Yet Callisto possesses its own unique importance. Its surface is one of the most heavily cratered places in the solar system. Looking at Callisto is like looking back through time. Ancient impacts remain preserved across vast regions. Some features date back billions of years. Unlike Io, which constantly renews itself, Callisto preserves its history. It acts as a geological archive, a record keeper, a witness to events that occurred when the solar system was still young. Scientists sometimes describe worlds like this as time capsules. Callisto may not be dramatic, but it is invaluable. Without places like Callisto, much of the solar system's earliest history would be far harder to reconstruct. Leaving Jupiter behind, we arrive at Saturn, and here we encounter Titan. Titan deserves special attention because it is arguably one of the strangest regular moons ever discovered. Imagine standing on a moon where rivers flow, rain falls, clouds drift overhead, lakes gather in lowlands, wind shapes landscapes. At first, that description sounds almost Earth-like. Then comes the twist. The rivers aren't water, the lakes aren't water, the rain isn't water. They're hydrocarbons, methane and ethane. Titan is so cold that substances which exist as gases on Earth behave like liquids there. Entire weather systems operate using chemistry that would seem impossible on our planet. Meanwhile, beneath Titan's icy crust, evidence suggests another hidden ocean may exist. Titan effectively contains two very different environments at once. A complex surface weather system above, a potential liquid water ocean below. No other moon combines those characteristics quite the same way. Its thick atmosphere makes it even more unusual. Most moons have little atmosphere or none at all. Titan possesses one denser than Earth's. If you stood on Titan's surface, atmospheric pressure would not be your biggest problem. The temperature would. The moon is astonishingly cold. Still, Titan remains one of the most intriguing destinations for future exploration. Many scientists consider it a natural laboratory for studying chemistry that may resemble conditions from Earth's distant past. Next, let's visit Uranus. Its regular moons receive less attention than Jupiter's or Saturn's, but they are fascinating worlds nonetheless. Titania is the largest. Its surface contains enormous fault systems stretching across great distances. These fractures suggest the moon expanded internally at some point in its history. Imagine an entire world slowly cracking as internal processes reshaped it. That's the story Titania appears to tell. Nearby is Oberon, dark, heavily cratered, and ancient. Oberon spends much of its existence in the outer reaches of Uranus's moon system. It receives little sunlight. Temperatures remain extremely low. Yet even this distant world preserves evidence of geological activity that may have occurred long ago. Then comes Umbriel. Among Uranus's major moons, Umbriel is often considered the darkest. Not evil, not mysterious in a dramatic science fiction sense, simply dark. Its surface reflects relatively little sunlight. For years, scientists struggled to understand why. Perhaps ancient impacts exposed darker material. Perhaps space weathering altered the surface. The exact story remains uncertain. Even today, Umbriel keeps some of its secrets. Ariel provides a sharp contrast. It is brighter, younger looking, more heavily shaped by geological processes. Valleys, ridges, and signs of resurfacing suggest a more active past. If Umbriel resembles an elderly historian preserving ancient records, Ariel appears more like a world that spent longer reinventing itself. And finally, there is Miranda. Miranda might be the strangest of Uranus's regular moons. When spacecraft first returned detailed images, scientists were astonished. Parts of Miranda looked as though someone had assembled it from mismatched pieces. Different terrains sat side by side in seemingly chaotic arrangements. Enormous cliffs towered across the landscape. Some regions appeared dramatically different from neighbouring areas. One possibility is that Miranda suffered catastrophic disruption long ago. Perhaps it was shattered and later reassembled by gravity. Whether that exact scenario occurred remains debated. What is certain is that Miranda refuses to behave like a simple, ordinary moon. Its appearance remains one of the most unusual in the solar system. Looking across all these worlds together reveals something remarkable. They share a common origin. They formed alongside their parent planets. They belong to the same broad family, and yet their outcomes differ enormously. Io became volcanic. Europa hid an ocean. Ganymede grew enormous. Callisto preserved history. Titan developed weather. Miranda evolved into something bizarre. The differences emerged because location matters, size matters, composition matters, gravitational interactions matter. A moon story does not end when it forms. Formation is merely the beginning. Billions of years of evolution follow. Heat flows. Impacts occur. Orbits shift. Internal oceans emerge. Volcanoes erupt. Surfaces crack. Entire worlds transform. That's one of the reasons moons are so valuable scientifically. They allow us to watch how similar beginnings can produce dramatically different outcomes. Nature starts with familiar ingredients, then time does the rest. Not every moon gets the privilege of a stable beginning. Some form alongside their planets, growing slowly from the same disk of material that surrounds a young world. Those moons spend billions of years following predictable paths, like lifelong residents who have never left their hometown. Others have much stranger histories. They began somewhere else entirely. They wandered. They drifted through space. And at some point, gravity stepped in and changed everything. These are the captured moons. If the regular moons are the native inhabitants of planetary systems, captured moons are immigrants. They weren't born where we find them today. Instead, they arrived from distant regions of the solar system and somehow became trapped by the gravity of a larger world. That raises an obvious question. How exactly does a planet capture a moon? At first glance, it seems impossible. Imagine throwing a baseball toward Earth. Gravity pulls it inward, but unless something removes energy from the system, the ball doesn't simply settle into orbit forever. It follows a path and eventually escapes or falls. The same principle applies in space. A wandering object passing near a planet should normally swing around it and continue on its way. Capturing a moon requires something more. Energy must be removed. The object's motion must change. The circumstances have to be just right. Sometimes another object participates in the encounter. Sometimes atmospheric drag helps. Sometimes gravitational interactions involving multiple bodies redistribute energy in complicated ways. Whatever the mechanism, successful capture appears to be relatively uncommon. That rarity is one reason captured moons are so interesting. They're survivors of unusual events. Each one represents a story that unfolded differently from the standard pattern. And among all captured moons in the solar system, none is more famous than Triton. Orbiting Neptune nearly 4.5 billion kilometers from the Sun, Triton stands out immediately because of the direction in which it travels. Most major moons orbit in the same direction their planets rotate. This makes sense if they formed from the same rotating disk. Triton doesn't. It moves backward. Astronomers call this a retrograde orbit. That single detail immediately raises suspicion. It's like arriving at a family reunion and discovering one person has a completely different surname, accent, and life story from everyone else. You start asking questions. The more scientists studied Triton, the stranger it became. Its orbit suggested capture. Its composition suggested capture. Its characteristics suggested capture. Eventually, the evidence became overwhelming. Triton almost certainly did not form around Neptune. Instead, it likely originated in the distant Kuiper belt, a region beyond Neptune populated by icy worlds and dwarf planets. In fact, Triton resembles Pluto in many ways. Both are icy. Both occupy the outer solar system. Both share similar sizes and compositions. If Triton orbited the Sun independently today, many people might view it as another dwarf planet. Instead, Neptune claimed it long ago. Exactly how this happened remains an active area of research. One leading theory suggests Triton was originally part of a binary system. Picture two icy worlds orbiting one another while travelling through the outer solar system. As they passed near Neptune, the planet's gravity disrupted the pair. One object escaped. The other lost enough energy to become trapped. That trapped object became Triton. It's an elegant explanation, and it fits the evidence remarkably well. The consequences of that capture were enormous. Triton's original orbit was likely highly elongated and chaotic. Over immense periods of time, gravitational interactions gradually smoothed it into the more circular path we see today. Yet the process generated tremendous internal heating. Imagine constantly stretching and squeezing an entire moon. Heat builds, ice melts, internal structures change, geology becomes active. The result is a world that refuses to behave like a frozen relic. When Voyager 2 flew past Neptune in 1989, scientists expected an ancient icy moon covered with impact craters. Instead, Triton surprised everyone. Its surface appeared relatively young. There were vast frozen plains, strange ridges, complex terrain. Even more astonishing, Voyager observed active geysers. Dark plumes of material erupted from the surface and rose into the thin atmosphere. At the time, Triton became one of the very few worlds known to be geologically active. Again, a captured moon was proving more interesting than anyone expected. Triton remains one of the most compelling destinations for future exploration. Many planetary scientists would love to return. After all, how often do you get the opportunity to study what is essentially a captured dwarf planet orbiting the outermost giant planet? Not far from Triton, at least on a cosmic scale, lies another fascinating captured moon, Nereid. Nereid also orbits Neptune, but unlike Triton, it follows one of the most eccentric orbits known among major moons. At its closest point, it approaches Neptune relatively closely. At its farthest point, it travels dramatically farther away. Its orbit looks stretched almost to absurdity. Such behaviour immediately suggests a turbulent past. Nereid likely experienced major gravitational disruptions. Some researchers suspect Triton's arrival may have contributed. Imagine what happens when a massive captured moon suddenly enters an existing moon system. Orbits become disturbed. Gravitational interactions increase. Smaller moons may be scattered. Some may be lost entirely. Others may be pushed into unusual paths. Nereid could be a survivor of exactly that kind of ancient upheaval. If so, it represents evidence of a dramatic restructuring event that occurred billions of years ago. A witness to Neptune's chaotic past. Moving inward through the solar system brings us to Saturn. Most people associate Saturn with its rings, and understandably so. They are magnificent. Yet Saturn also possesses an enormous collection of moons. Among them is Phoebe. Phoebe is peculiar. While many of Saturn's major moons follow orderly, regular orbits, Phoebe does not. Like Triton, Phoebe travels in a retrograde direction. That immediately suggests it wasn't born alongside Saturn. Its appearance strengthens the case. Phoebe is dark, very dark, much darker than many neighbouring moons. Rather than resembling Saturn's regular icy satellites, Phoebe looks more like an object from the outer solar system. Its composition supports this idea. Scientists believe Phoebe may have originated among populations of icy bodies far beyond Saturn before eventually being captured. In other words, Saturn may have acquired Phoebe the way Neptune acquired Triton. Through gravitational opportunity. Phoebe is much smaller than Triton, of course. Its diameter is only about 213 kilometers. Yet size doesn't determine scientific importance. Phoebe offers researchers a chance to study material that may preserve conditions from the solar system's earliest eras. Its heavily cratered surface acts like a historical archive. Every impact records part of a story stretching back billions of years. Interestingly, Phoebe contributes material to Saturn's enormous and faint Phoebe ring. Dust gradually escapes from the moon and spreads into a vast ring system. That ring is so enormous that if visible to human eyes, it would appear larger than many full moons in the sky. Fortunately for our neck muscles, it remains invisible without specialized instruments. Phoebe reminds us that captured moons don't simply sit quietly in orbit. They continue influencing their surroundings. They remain active participants in planetary systems. Now let's travel much closer to home. Mars possesses two small moons, Phobos and Deimos. At first glance, they seem obvious candidates for capture. Both are tiny. Both have irregular shapes. Neither resembles a spherical world like Earth's moon. Instead, they look somewhat like oversized asteroids. For decades, many scientists assumed that was exactly what they were, captured asteroids. The idea seemed straightforward. Mars sits relatively close to the asteroid belt. Numerous rocky bodies travel through the region. Surely Mars simply captured a pair. Problem solved. Except science rarely leaves things that simple. As researchers gathered more data, questions emerged. The moon's orbits are surprisingly circular. They're also remarkably aligned with Mars's equator. Captured objects often retain more irregular orbital characteristics. Yet Phobos and Deimos appear unusually well behaved. That doesn't mean they weren't captured. It simply complicates the story. Today, scientists continue debating their origins. Some evidence supports capture. Other evidence suggests they may have formed from debris produced by a massive impact on Mars. In other words, they might not be captured moons at all. The mystery remains unresolved. Even so, they provide an excellent opportunity to explore how difficult it can be to reconstruct ancient histories. Not every moon arrives with a neat explanation attached. Sometimes the evidence points in multiple directions. Sometimes nature refuses to provide clear answers. Phobos is especially intriguing. It orbits incredibly close to Mars, so close that it circles the planet faster than Mars rotates. As a result, Phobos rises in the west and sets in the east. That's already unusual. Its future is even stranger. Unlike our moon, which gradually moves away from Earth, Phobos is slowly spiraling inward. Mars's gravity is drawing it closer over time. Eventually, one of two outcomes will occur. Either Phobos will crash into Mars, or tidal forces will tear it apart before impact. If the latter happens, Mars may briefly gain a ring system formed from the moon's remains. Imagine future observers watching a ring form around Mars because an entire moon was pulled apart by gravity. The solar system remains capable of surprising us. Deimos, meanwhile, occupies a more distant orbit. It is smaller and less dramatic than Phobos, yet it shares the same basic mystery. Captured asteroid, impact-generated moon, something else entirely. The answer remains uncertain, and uncertainty often drives science forward. The most interesting questions are frequently the ones we haven't solved yet. When viewed together, Triton, Phoebe, Nereid, Phobos and Deimos reveal something important. Planetary systems are not closed environments. Worlds move, objects migrate. Gravity reshuffles the architecture of the solar system. A moon seen today may not have started where it currently resides. In fact, some moons are living proof that planets occasionally acquire entirely new companions. That's a fascinating idea. We often imagine the solar system as stable and orderly. The planets orbit the sun. The moons orbit the planets. Everything seems fixed. But the reality is more dynamic. The early solar system was crowded. Objects frequently interacted. Collisions occurred. Near misses happened. Gravitational encounters altered countless trajectories. Some worlds were ejected, others were captured. Entire histories changed because two objects happened to pass near one another at exactly the right moment. Captured moons preserve evidence of that ancient chaos. They're reminders that planetary systems evolve, not just during formation, but long afterward. Some moons follow the rules. They orbit close to their planets. Their paths are nearly circular. They move in the same direction as the planet's rotation. Their behaviour is orderly enough that astronomers can often predict their positions centuries into the future with remarkable accuracy. And then there are the irregular moons. If regular moons resemble long-term residents who have spent their entire lives in the same neighbourhood, irregular moons are the mysterious newcomers who arrive from somewhere else, settled into unusual routines, and never quite blended in. The term irregular moon sounds almost casual, but it describes a very specific type of object. These moons generally orbit far from their parent planets. Their paths are often highly tilted, noticeably elongated, and sometimes even retrograde, meaning they travel opposite the direction of the planet's rotation. When astronomers see these characteristics, they immediately become suspicious. Something unusual happened here. The reason is simple. Regular moons tend to form from the disk of material surrounding a young planet. Because everything in that disk is rotating in roughly the same direction, the resulting moons inherit orderly orbits. Irregular moons don't fit that pattern. Their paths look more like the aftermath of a complicated gravitational accident. Most scientists believe many irregular moons began life elsewhere before being captured. Some may have originated in the asteroid belt. Others may have come from distant icy regions beyond the giant planets. A few might even be fragments of larger bodies that broke apart after capture. Whatever their exact origins, irregular moons represent some of the solar system's greatest orbital oddities. Let's begin with one of the most famous examples, Himalaya. Orbiting Jupiter, Himalaya is the largest member of a group of moons known as the Himalaya Group. With a diameter of roughly 140 kilometers, it's substantial enough to stand out among Jupiter's numerous irregular satellites. When Himalaya was discovered in 1904 by Charles Dillon Perrine, it immediately expanded humanity's understanding of Jupiter's moon system. Unlike the large Galilean moons, Himalaya travels much farther from Jupiter. Its orbit is noticeably inclined relative to Jupiter's equator, and its characteristics strongly suggest it did not form alongside the giant planet. Many astronomers suspect Himalaya may be the surviving fragment of a larger captured object that broke apart long ago. If that's true, then several smaller moons travelling in similar orbits may actually be siblings, pieces of the same ancient body scattered by a collision. Imagine discovering that multiple moons are really fragments of one world that shattered billions of years ago. The solar system keeps records in unusual ways. Another fascinating Jovian irregular moon is Pasiphae. Pasiphae is particularly interesting because it moves in a retrograde orbit. Instead of travelling in the same direction as Jupiter's rotation, it goes the opposite way. That alone makes it stand out. Its orbit is also highly inclined and significantly eccentric. In simple terms, Pasiphae follows a path that looks far less organised than those of Jupiter's regular moons. Astronomers believe Pasiphae may be the largest member of another moon family, created when a captured object broke apart. If so, many of Jupiter's irregular moons may share common ancestry. Rather than being individual captures, they may represent fragments of larger captured worlds. This idea reveals something important. Capture is often only the beginning of the story. Once trapped, moons can collide. They can fragment. They can create entire populations of smaller satellites. A single capture event may ultimately produce dozens of moons. Jupiter, with its enormous gravity, appears particularly skilled at collecting these cosmic leftovers. Moving outward to Saturn, we encounter another famous irregular moon, Ymir, named after a giant from Norse mythology. Ymir follows a retrograde orbit far from Saturn. Discovered in 2000, Ymir belongs to a growing population of irregular moons that astronomers have identified using modern telescopes. What's remarkable about Ymir is not just its orbit, but what its existence implies. For centuries, Saturn appeared to have only a handful of known moons. Today, improved observations reveal an enormous and complicated satellite system containing dozens upon dozens of irregular objects. Many are tiny, many are dark, many likely originated as captured bodies. Ymir represents part of that hidden population, a reminder that the giant planets continue to reveal new members of their families long after we thought we understood them. Its path around Saturn is highly inclined and retrograde, characteristics entirely consistent with capture. If Ymir could tell its story, it might begin in a completely different region of the solar system, before Saturn's gravity permanently altered its future. Another Saturnian irregular moon worth visiting is Scarthy. Like Ymir, Scarthy travels on a distant and highly tilted orbit. Its journey around Saturn takes hundreds of Earth days. Because of its small size and great distance from the planet, it remained undiscovered until the 21st century. That's one of the fascinating things about irregular moons. Many are difficult to find. They are often small, dark, and far from the bright planets they orbit. Detecting them requires powerful telescopes, careful observations, and a great deal of patience. Every new discovery helps astronomers reconstruct the history of planetary capture events. Each moon acts like a clue in a detective story billions of years old. Then there is Sycorax. Orbiting Uranus, Sycorax is one of the largest irregular moons known around that planet. Discovered in 1997, it immediately attracted attention because of its unusual orbit. Unlike Uranus's major regular moons, Sycorax travels far from the planet and follows a strongly inclined path. Everything about its motion suggests an external origin. Today, Sycorax is considered one of the best examples of an irregular satellite around Uranus. Its existence also highlights an important reality. The giant planets all seem to possess irregular moon populations. Jupiter has them, Saturn has them, Uranus has them, Neptune has them. This pattern strongly suggests capture was a common process during the solar system's early history. The planets weren't merely forming, they were collecting, sometimes intentionally, in a gravitational sense, sometimes accidentally. Either way, they were acquiring new companions. Neptune offers another excellent example in the form of Halimede. This small irregular moon follows a distant retrograde orbit and may be related to Nereid through an ancient collision. Some studies suggest similarities in their appearance and orbital characteristics. If that interpretation is correct, Halimede may represent a fragment of a larger object involved in a violent event long ago. Again, we encounter a recurring theme: capture, collision, fragmentation. The history of irregular moons is often far messier than the history of regular moons, and perhaps that's why scientists find them so valuable. Regular moons tell us about planetary formation. Irregular moons tell us about everything that happened afterward. They preserve evidence of migration, encounters, impacts, and gravitational disruptions. They reveal a solar system that was once far more chaotic than it appears today. Imagine the early era of the giant planets. Countless icy bodies moved through space, Some passed safely by, some collided, some were scattered outward. Others were thrown inward. A fortunate few crossed paths with giant planets under exactly the right conditions. Those became captured moons. The survivors still orbit today, not because they were supposed to, not because nature planned it that way, simply because gravity happened to win. Their odd orbits preserve that history. Every extreme tilt, every elongated path, every retrograde motion. Each serves as evidence that these worlds followed a different journey. Astronomers often classify irregular moons into families. These families consist of moons with similar orbital characteristics. The logic is straightforward. If several moons share nearly identical paths, they may once have been part of the same larger object. A collision shattered the original body, producing numerous fragments that continued orbiting together. The Himalaya group around Jupiter is one example. The Pasiphae group is another. Saturn possesses multiple irregular families as well. Studying these groups allows researchers to reconstruct events that occurred billions of years ago. It's a bit like finding pieces of an ancient vase and attempting to rebuild the original shape. The task isn't easy. Many details remain uncertain. Yet each new observation adds another piece to the puzzle. What's particularly interesting is how these moons challenge our instinct to categorize everything neatly. When most people imagine a moon, they picture something like Earth's moon. Round, predictable, stable. The irregular moons refuse to cooperate with that image. Some look more like asteroids than moons. Some travel backward. Some occupy bizarrely tilted orbits. Some may be fragments of larger bodies. Others may be captured relics from regions far beyond their current homes. They're reminders that nature does not prioritize simplicity. Given enough time, gravity creates complexity. And nowhere is that complexity more visible than in the giant planet's collections of irregular satellites. If irregular moons are the solar system's wanderers, arriving from distant places and settling into unusual orbits, then shepherd moons are something entirely different. They are caretakers, not because they choose to be, not because they possess any awareness of what they're doing, but because gravity has assigned them a very specific job. A shepherd moon is a small moon whose gravity helps shape, maintain, and organize a planetary ring system. Without these moons, many rings would look completely different. Some gaps would disappear, some edges would blur, some structures might never exist at all. At first glance, that may sound surprising. After all, when people think about Saturn's rings, they usually imagine vast collections of ice particles stretching across space. The ring seems so enormous that tiny moons should be insignificant by comparison. Yet gravity doesn't care about appearances. Even a relatively small moon can influence countless particles over time, and when billions upon billions of particles respond to the same gravitational nudges, remarkable things happen. To understand shepherd moons, imagine a crowd of runners moving around a circular track. Left alone, the runners gradually spread out. Some move faster, some move slower. The group becomes less organized. Now imagine placing coordinators along the track who gently guide the runners back into position. Order emerges. The group maintains its shape. That's roughly what shepherd moons accomplish within planetary rings. Their gravity continually interacts with ring particles, helping preserve structures that might otherwise dissolve. The best place to see this process is Saturn. Saturn's rings are so spectacular that they almost seem unreal. Even through a modest telescope, they transform Saturn from a distant planet into something unforgettable. Yet what appears smooth and continuous from afar is actually astonishingly complex. The rings contain countless gaps, waves, strands, and structures. Some are shaped by large moons. Others are maintained by tiny shepherd moons operating like celestial traffic managers. One of the most famous examples is Pan. Pan is a small moon orbiting within Saturn's A-ring. It resides inside a gap known as the Encke Gap. The gap itself is roughly 325 kilometers wide, and Pan travels directly through its center. When spacecraft first returned detailed images, Pan immediately became a favourite among planetary scientists, partly because of its role, partly because of its appearance. Pan looks unusual, extremely unusual. Its equatorial ridge gives it the appearance of a ravioli floating through space. Not the most intimidating description for a moon, admittedly. But science is occasionally forced to work with whatever comparisons nature provides. That ridge likely formed from ring material slowly accumulating around the moon. As Pan orbits Saturn, its gravity pushes nearby particles away from its path. The result is a maintained gap. Without Pan, the Enki gap would likely look very different. The moon effectively acts as a ring sculptor, not by forcefully clearing material all at once, but through countless gravitational interactions repeated over immense spans of time. Another remarkable shepherd moon is Daphnis. Daphnis occupies the Keeler Gap, another opening within Saturn's rings. Unlike Pan, Daphnis is even smaller. Its diameter is only about 8 kilometers. You could fit it comfortably inside many major cities. Yet despite its modest size, Daphnis creates some of the most beautiful structures in Saturn's rings. As it moves through the gap, its gravity generates waves along the edges. Ring particles rise and fall, creating rippling patterns that resemble wakes trailing behind a boat moving through water. The images returned by the Cassini-Huygens mission revealed these structures in extraordinary detail. For the first time, scientists could watch a tiny moon actively shaping an enormous ring system. It was a vivid demonstration of how powerful gravity can be, even when the object generating it is relatively small. Imagine a moon only a few kilometers across influencing structures stretching for hundreds of kilometers. Space frequently rewards patience. Small forces acting continuously often achieve astonishing results. Then there are Prometheus and Pandora. These two moons operate as a pair around Saturn's narrow F-ring. If Saturn's main rings are broad highways of icy particles, the F-ring is more like a winding country road. It is narrow, dynamic, and surprisingly complicated. Prometheus orbits just inside the ring. Pandora travels just outside it. Together they help confine ring particles between them. The arrangement resembles two shepherd dogs guiding a flock from opposite sides. In fact, this analogy inspired the term shepherd moon in the first place. As the moons move, their gravity continuously perturbs ring particles. Some particles get pulled inward, others get pushed outward. The result is a ring that maintains its overall structure despite constant disruption. Yet the process isn't perfectly orderly. Prometheus in particular creates striking features. As it approaches portions of the F-ring, its gravity draws material outward, producing streamers and channels. The ring briefly appears torn apart before gravity gradually smooths things again. Watching simulations of these interactions feels almost like watching a living system. Everything moves, everything responds, nothing remains static. The rings are not frozen structures. They are active environments constantly shaped by gravitational influences. One reason shepherd moons fascinate astronomers is that they reveal something important about planetary rings themselves. For centuries, rings appeared simple, elegant perhaps, but simple. A planet surrounded by a flat disk. Modern observations tell a different story. Rings are ecosystems of motion. Particles collide. They clump together. They spread apart. Gravitational forces compete constantly. And shepherd moons play a major role in maintaining order within that chaos. In some cases, these moons may even provide clues about how larger structures form elsewhere in the universe. The same gravitational principles that shape rings also influence protoplanetary disks around young stars. Those disks eventually create planets. In a way, shepherd moons allow scientists to observe similar processes on a smaller and more accessible scale. The physics repeats itself, only the sizes change. Interestingly, Saturn is not the only planet with shepherd moons. Uranus possesses them as well. Its ring system is much darker and less famous than Saturn's. but it contains several narrow rings whose structures are influenced by nearby moons. One notable example involves Cordelia and Ophelia. These small moons help maintain Uranus's Epsilon ring, the brightest of the planet's ring system. Like Prometheus and Pandora, they orbit on opposite sides of the ring. Their combined gravitational effects help keep ring material confined. Without those influences, the ring would gradually spread out over time. Again, tiny moons preserve larger structures through persistence rather than power. The lesson appears repeatedly throughout planetary science. Small forces applied continuously can reshape entire systems. Neptune may offer additional examples. Its rings are faint and difficult to observe, but evidence suggests gravitational interactions with nearby moons influence their structure. Researchers continue studying these systems because many details remain uncertain. Even after decades of spacecraft exploration and telescope observations, ring dynamics remain surprisingly complicated. Part of the challenge comes from scale. A ring may contain trillions of particles. Each responds to gravity. Each follows its own orbit. Each can collide with neighbouring particles. Trying to model everything simultaneously becomes extraordinarily difficult. Shepherd moons add another layer of complexity. Yet they also help explain features that would otherwise remain mysterious. For example, why do certain ring edges remain so sharply defined? Why don't particles simply spread out and blur those boundaries? Why do some gaps persist for millions of years? Why do certain waves appear repeatedly? The answer often leads back to nearby moons. The moons may be small, their influence may seem subtle, but over time, subtle influences become dominant influences. There's something else that makes shepherd moons particularly interesting. They occupy a curious middle ground between moons and rings. Some may have formed from ring material. Others may contribute material back into the rings. The distinction isn't always clear. Imagine a ring particle colliding with others. Gradually a clump forms. That clump grows. Eventually it becomes a moonlet. Given enough time, perhaps it becomes a shepherd moon. Now imagine impacts eroding that moon. Material escapes. Some of it returns to the rings. The cycle continues. In that sense, rings and shepherd moons are deeply connected. They are not entirely separate entities. They are parts of the same gravitational environment. Studying one helps scientists understand the other. The Cassini-Huygens mission transformed our understanding of these relationships. Before Cassini arrived at Saturn in 2004, many questions remained unanswered. After years of observations, the spacecraft revealed a system far more dynamic than anyone anticipated. Shepherd moons weren't merely maintaining ring structures, they were actively creating features, generating waves, carving gaps, and reshaping their surroundings. Some interactions changed noticeably over relatively short periods. On cosmic timescales, the rings were alive with activity. That realization altered how scientists viewed ring systems throughout the solar system. Rather than static decorations, rings became dynamic laboratories where gravity could be studied in action, and shepherd moons emerged as some of the most important participants. What's especially remarkable is how easy it is to overlook them. When people admire Saturn through a telescope, they notice the rings immediately. Very few notice Pan, or Daphnis, or Prometheus, or Pandora. The stars of the show appear to be the rings themselves, yet much of what makes those rings beautiful depends on the invisible work of tiny moons. They're the stage hands of the solar system, rarely noticed, absolutely essential. By now, we've encountered moons that formed alongside their planets, moons that were captured from elsewhere, and moons that quietly sculpt entire ring systems through gravity alone. Most of those worlds, despite their differences, share one comforting characteristic. Their motions are predictable. Given enough mathematical patience and a sufficiently large whiteboard, astronomers can calculate where they'll be tomorrow, next year, or even centuries from now. But not every moon is so cooperative. Some inhabit gravitational environments so complicated that their rotations and movements become extraordinarily difficult to predict. These are the chaotic moons. The name sounds dramatic, and for once, astronomy isn't exaggerating. In science, chaos doesn't necessarily mean randomness. Instead, it refers to systems that are extremely sensitive to small influences. Tiny differences can produce vastly different outcomes over time. A chaotic system follows the laws of physics perfectly, yet becomes incredibly difficult to forecast far into the future. Weather provides a familiar example. The atmosphere obeys physical laws, but predicting exact conditions months ahead becomes challenging because small changes grow into larger ones. Certain moons experience something similar. Their worlds are governed by gravity, but the details of their motion can become surprisingly complex. Among all known examples, one moon stands above the rest as the poster child for orbital unpredictability. Hyperion. Orbiting Saturn, Hyperion looks less like a moon and more like a cosmic sponge. Its surface is covered with deep craters and strange cavities, giving it an appearance unlike almost anything else in the solar system. The first images returned by spacecraft left many scientists staring at photographs and wondering whether nature had somehow decided to experiment with abstract sculpture. Hyperion's appearance alone would make it memorable. Its behaviour makes it legendary. Most large moons rotate in a stable fashion. One side gradually faces a particular direction. The rotation is orderly, predictable, reliable. Earth's moon is a perfect example. It keeps the same face pointed toward Earth because it is tidally locked. Hyperion refuses to behave that way. Instead, it tumbles, not metaphorically, literally tumbles. Imagine throwing an oddly shaped rock into the air. It spins unpredictably, changing orientation continuously. That's essentially what Hyperion does. As it orbits Saturn, its rotation changes in ways that are remarkably difficult to predict. This happens because of several factors working together. First, Hyperion is irregularly shaped. Unlike a sphere, it has an uneven structure that responds differently to gravitational forces depending on its orientation. Second, it experiences strong gravitational influences from nearby Titan, Saturn's largest moon. The interaction creates repeated disturbances. Over time, those disturbances accumulate. The result is chaotic rotation. If you landed on Hyperion and somehow survived the practical difficulties involved, the sky would behave strangely. Saturn might appear in one direction. Hours later, it could seem to shift unexpectedly. The orientation of the surface relative to space changes continually. There is no stable, familiar rhythm. Hyperion effectively rolls through space. For planetary scientists, it was a remarkable discovery. Before Hyperion, many assumed large moons would eventually settle into predictable rotational patterns. Hyperion demonstrated that nature had other ideas. Interestingly, Hyperion isn't unique because of some mysterious force. The laws governing its motion are well understood. The challenge comes from prediction. The further into the future scientists attempt to calculate its exact orientation, the more uncertainty grows. Tiny differences become amplified. This is chaos in its scientific sense. Perfectly lawful, exceptionally difficult to forecast. Hyperion reminds us that predictability and determinism are not always the same thing. The universe can obey precise rules while still producing behaviour that appears wildly complicated. Another fascinating example comes from Saturn's moon system as well, Janus and Epimetheus. At first glance, these two moons seem fairly ordinary. Neither is particularly large. Neither possesses volcanoes, oceans, or thick atmospheres. Yet together they perform one of the strangest orbital dances in the solar system. Janus and Epimetheus orbit Saturn at nearly the same distance. This should be a problem. Normally, two moons sharing almost identical orbits would eventually collide or gravitationally scatter one another. Instead, they engage in an elegant exchange. Every few years, as one moon catches up with the other, gravity alters their paths. The inner moon moves outward, the outer moon moves inward. Effectively, they swap places. Then the process repeats, again and again. Imagine two runners sharing nearly the same lane around a track. Every time they approach each other, they somehow exchange positions without crashing. It sounds impossible. Yet Janus and Epimetheus have been doing exactly that for countless millions of years. Their motions are stable overall, but the details reveal a level of orbital complexity rarely encountered elsewhere. Astronomers love these moons because they demonstrate how surprisingly creative gravity can be. Even seemingly impossible arrangements can persist if the conditions are just right. Moving farther outward, we encounter another world often associated with unusual orbital behaviour: Nereid. We've already met Nereid as one of Neptune's irregular moons, but it deserves another mention here because of its extraordinarily eccentric orbit. Unlike most major moons, which follow relatively circular paths, Nereid's orbit is stretched dramatically. At some points it approaches Neptune much more closely. At others, it travels vastly farther away. This means the gravitational environment experienced by Nereid changes substantially throughout its journey. Scientists suspect its unusual path may be linked to Neptune's capture of Triton long ago. When Triton arrived, the entire moon system may have been thrown into turmoil. Existing moons could have been scattered, disrupted, or ejected. Nereid may be one of the survivors. Its current orbit acts like a fossil record of that ancient chaos. In a sense, Nereid carries evidence of a gravitational catastrophe that occurred billions of years ago, and while its motion is not chaotic in exactly the same sense as Hyperion's tumbling rotation, it belongs to a broader family of moons whose histories were shaped by instability and dramatic orbital evolution. The story becomes even more interesting when scientists use computer simulations. Modern models allow researchers to recreate ancient moon systems and watch how they evolve. Sometimes the simulations reveal stable arrangements. Sometimes they reveal instability. Occasionally they produce astonishing results. Moons collide, orbits cross, objects are ejected entirely. New configurations emerge. These experiments suggest that today's orderly-looking solar system may once have been significantly messier. Many chaotic situations likely resolved themselves long ago. The moons we see today are survivors. That realization changes how we think about planetary systems. When we look at Jupiter's moons lined up neatly around the giant planet, it's tempting to assume things have always been that way. The evidence suggests otherwise. Early planetary systems may have resembled construction sites more than finished architecture. Objects moved, worlds interacted, gravity constantly rearranged the furniture. Some moons ended up in stable positions, others did not. In fact, some researchers believe entire populations of ancient moons may have disappeared through collisions or ejections. The current systems could represent only a fraction of what once existed. That's a humbling thought. The solar system we know may be the result of billions of years of gravitational selection. The stable arrangements survived. The unstable arrangements vanished. Yet even today, examples like Hyperion preserve reminders that chaos never disappears entirely. It remains present, waiting in the details. One reason chaotic moons fascinate scientists is that they help test theories of celestial mechanics. Gravity is one of the most familiar forces in nature. Objects fall, planets orbit, moons circle their worlds. Everything seems straightforward. Then you encounter a system where multiple gravitational influences interact simultaneously. Suddenly, the mathematics becomes far more complicated. Chaotic moons provide natural laboratories for studying these effects. By observing them, researchers learn how orbital systems evolve. They learn how stability emerges, they learn how instability develops, and they gain insights that apply far beyond moons themselves. The same principles help explain planetary systems around distant stars. They help explain asteroid populations. They help explain the formation and evolution of galaxies. A tumbling moon around Saturn may seem like a niche topic, but the underlying physics connects to some of the largest questions in astronomy. There is also something strangely relatable about chaotic moons. Most celestial objects appear orderly, predictable, disciplined. The planets follow their orbits with remarkable consistency. The stars rise and set according to reliable schedules. Then along comes Hyperion, tumbling through space like it forgot to read the instruction manual. It serves as a useful reminder that nature contains exceptions. Not everything settles neatly into place. Not every system achieves perfect regularity. Sometimes the universe embraces complexity, and occasionally that complexity becomes the most interesting part of the story. Yet despite all their unpredictability, chaotic moons are still fundamentally shaped by gravity. Gravity drives their rotations. Gravity shapes their orbits. Gravity determines their futures. The same force that creates instability can also create extraordinary activity. Few places in the solar system seem less likely to host volcanoes than moons. When most people picture a moon, they imagine a cold, silent world covered in impact craters. A place where geological activity ended billions of years ago. A place where nothing much happens anymore. That assumption seems reasonable. After all, moons are generally smaller than planets. Smaller worlds tend to cool more quickly. Their interiors lose heat. Their geology slows down. Eventually, they become inactive. At least that's what scientists once thought. Then spacecraft started visiting the outer solar system, and one moon completely overturned expectations. Its name is Io. Orbiting Jupiter alongside Europa, Ganymede and Callisto, Io initially appeared to be just another member of the Galilean moon family. It was large. It orbited a giant planet. It reflected sunlight. Nothing about it immediately suggested it would become one of the most extraordinary worlds ever discovered. Then came 1979. When the spacecraft Voyager 1 flew past Jupiter, scientists expected to see an ancient surface covered with countless craters. Instead, they found something nobody had anticipated. Volcanoes. Active volcanoes. Enormous volcanoes. The discovery was so unexpected that at first some researchers thought there might be an error in the data. Yet the evidence was unmistakable. Gigantic plumes rose hundreds of kilometers above the surface. Fresh lava flows covered large regions. Entire landscapes appeared geologically young. The reason was astonishingly simple. Io was being squeezed, constantly, relentlessly, by gravity. To understand why Io is so active, imagine repeatedly bending a metal wire. The more you bend it, the warmer it becomes. Energy is being converted into heat. Now replace the wire with an entire moon. That's essentially what Jupiter does to Io. Jupiter's gravity is immense, far stronger than anything Earth experiences from the moon. As Io travels around Jupiter, tidal forces continuously stretch and compress the moon. The process is called tidal heating, and it generates extraordinary amounts of internal energy. The situation becomes even more intense because of Io's neighbouring moons. Europa and Ganymede exert gravitational influences of their own. Together they prevent Io's orbit from becoming perfectly circular. That small detail matters enormously. If Io followed a perfectly circular path, tidal heating would weaken considerably. Instead, the orbit remains slightly elliptical. The amount of gravitational squeezing changes continuously. The moon flexes, its interior heats, volcanoes erupt, the cycle continues for billions of years. As a result, Io has become the most volcanically active world known. Not moon, world. Earth has volcanoes. Venus likely has volcanic activity. Mars possessed major volcanism in the past, yet none of them currently match Io's intensity. Hundreds of volcanic centers have been identified across its surface. Some eruptions produce lava fountains that would dwarf anything witnessed in human history. Others create enormous deposits of sulfur compounds that paint the landscape in vivid colors. That's one reason Io looks so unusual. Instead of the familiar grey appearance associated with many moons, Io displays yellows, oranges, reds, blacks and whites. Sulfur and sulfur dioxide dominate much of the surface. The result resembles a world designed by someone who felt ordinary. Geology was simply too boring. Standing on Io would be impossible for numerous reasons. The radiation environment alone would be lethal. The volcanic activity would present additional challenges. The terrain changes continuously. Fresh lava flows emerge. Plumes deposit new material. Entire regions undergo transformation. In many places, impact craters struggle to survive because geological activity erases them. That's one of the key signs scientists use when studying planetary surfaces. Young surfaces have fewer craters. Old surfaces accumulate more. Io's surface remains remarkably young because volcanism keeps resetting the clock. Every eruption rewrites part of the landscape. It's a world under constant renovation. Yet the story of volcanic moons does not begin and end with Io. Far from it. Once scientists understood tidal heating, they realized similar processes could affect other moons as well. Not always producing volcanoes exactly like Io's, but generating internal activity nonetheless. One fascinating example is Triton. We've already met Triton as Neptune's captured moon. At first glance, Triton seems an unlikely candidate for geological activity. It orbits far from the Sun. Temperatures are extraordinarily low. Sunlight is weak. Everything about the environment suggests stillness, and yet Voyager 2 observed active plumes rising from the surface. The mechanism differs somewhat from Io's volcanism. Instead of molten rock erupting from deep within the moon, Triton appears capable of producing cryovolcanic activity. The term sounds complicated, but the concept is straightforward. Cryovolcanism is often described as ice volcanism. Rather than erupting molten rock, these systems release materials such as water, ammonia, nitrogen, or methane. In extremely cold environments, those substances can behave somewhat like lava behaves on Earth. The temperatures are different, the chemistry is different, the appearance is different, but the underlying principle remains familiar. Material from below reaches the surface, the moon changes, geological activity continues. This idea of cryovolcanism opens an entirely new category of planetary behavior. When most people hear the word volcano, they immediately imagine lava. The solar system is more creative than that. On some worlds, ice can play a similar role. In these environments, geological activity becomes possible even where traditional volcanism would seem impossible. That realization transformed how scientists think about moons. Suddenly, geological activity was no longer restricted to warm rocky worlds. Cold icy moons could be active too. Enceladus provides another spectacular example. Orbiting Saturn, Enceladus initially appeared rather ordinary. It is relatively small. Its surface is bright and icy. Nothing about its appearance immediately suggested major discoveries. Then the spacecraft Cassini-Huygens arrived, and everything changed. Near Enceladus's south pole, scientists discovered gigantic plumes erupting into space. These weren't tiny geysers. They were massive jets of water vapor, ice particles, and other materials shooting outward from fractures in the crust. Some of that material escaped entirely. Some fell back to the surface. Some contributed directly to Saturn's E-ring. For the first time, researchers could observe a moon actively ejecting material into space. It was an extraordinary discovery. The plumes also revealed something even more exciting. Liquid water existed beneath the surface. Enceladus possesses a global ocean hidden below its icy crust. And where there is liquid water, scientific curiosity immediately follows. Today, Enceladus is considered one of the most promising places to search for signs of extraterrestrial life. Not because life has been found, it hasn't, but because the moon appears to possess several ingredients associated with habitable environments: liquid water, energy sources. Complex chemistry. Those ingredients continue attracting intense scientific interest. Strictly speaking, Enceladus belongs more to the category of cryovolcanic moons than traditional volcanic moons. Yet the distinction highlights an important point. The solar system contains many ways to remain active. Molten rock is only one possibility. As scientists continued exploring, they realized moons could remain geologically alive through multiple mechanisms: radiogenic heating, tidal heating, chemical interactions, internal oceans. Different worlds found different solutions. Another intriguing candidate is Europa. Europa is best known for its hidden ocean, but evidence suggests material from beneath the surface occasionally reaches upward. Researchers have observed possible plumes rising above the moon. The observations remain challenging and somewhat debated, but the possibility is exciting. If confirmed, Europa would join the growing list of worlds where subsurface material communicates with the exterior. That connection matters enormously. Without it, studying hidden oceans becomes extremely difficult. With it, future spacecraft may be able to sample material originating from beneath the ice without drilling kilometers downward. A remarkable shortcut if nature is kind enough to provide it. One lesson emerges repeatedly as we examine these moons. Activity does not necessarily require proximity to the sun. This realization was revolutionary. For much of scientific history, the sun seemed like the obvious source of planetary energy. Move farther away, become colder, become quieter. Yet moons such as Io and Enceladus demonstrate a different possibility. Gravity itself can power worlds. Tidal heating converts orbital energy into internal heat. As long as the gravitational interactions continue, geological activity can persist, in some cases for billions of years. It's a remarkable arrangement. A moon orbiting a giant planet effectively taps into a vast energy source. The giant planet's gravity becomes an engine. The moon becomes the beneficiary. The consequences can be dramatic. Volcanoes, geysers, cryovolcanism, hidden oceans, geological renewal. Entire environments emerge from what initially appears to be a simple orbital relationship. This has important implications beyond our solar system. If tidal heating can maintain activity on moons here, it may do the same elsewhere. Exomoons around giant planets could potentially experience similar processes. Some might possess subsurface oceans. Some might support long-term geological activity. Some could remain warm internally despite receiving little stellar energy. The universe suddenly becomes more interesting. Again, that's a recurring theme in astronomy. Every time scientists think they've identified the limits of possibility, nature quietly expands them. Volcanic moons are excellent examples. Nobody expected a moon to surpass Earth in volcanic activity. Nobody expected tiny icy moons to launch giant plumes into space. Nobody expected hidden oceans beneath frozen crusts. Yet, here we are. The evidence continues accumulating, and perhaps the most fascinating part is that volcanic activity represents only one outcome of internal heat. Not all moons advertise their secrets. Some worlds make their presence known immediately. Io erupts volcanoes visible from space. Titan wraps itself in a thick atmosphere. Earth's moon dominates our night sky. Ice moons are different. At first glance, they appear quiet, cold, inactive, the kind of places where nothing much happens anymore. Many of them sit far from the sun, where temperatures plunge to levels that would freeze almost anything solid. Their surfaces are covered in ice. Sunlight is weak. The landscape often appears pale and lifeless. For a long time, scientists assumed that was exactly what they were, frozen relics. The geological equivalent of abandoned buildings. Interesting perhaps, but largely inactive. Then spacecraft began arriving, and once again the solar system demonstrated its talent for making scientists look overly confident. Because beneath those frozen surfaces, Many ice moons turned out to be hiding extraordinary stories. Some conceal vast oceans, some remain geologically active, some possess surprisingly young terrain, and some may be among the most promising places to search for life beyond Earth. The remarkable thing is that none of this is obvious from the outside. An ice moon can appear completely frozen, while secretly maintaining an active interior. It is one of the greatest lessons planetary science has taught us over the last few decades. Never judge a world by its surface. Perhaps the best place to begin is Europa. We've already encountered Europa briefly when discussing Jupiter's regular moons, but no discussion of ice moons would be complete without it. Europa looks deceptively simple. Its surface is bright, smooth, covered by water ice. Compared to heavily cratered worlds, it almost appears unfinished. Yet that smoothness is itself a clue. Old surfaces accumulate craters, young surfaces do not. Something has been renewing Europa's exterior. Something has been erasing ancient impact scars. When scientists examined images from spacecraft such as Galileo, they noticed an intricate network of cracks stretching across the moon. Some extended for thousands of kilometers, others intersected one another in complicated patterns. The appearance resembled broken sea ice on Earth. That comparison turned out to be important. Researchers began asking a provocative question. What if Europa's icy crust floats on liquid water? The evidence gradually accumulated. Magnetic measurements, surface chemistry, geological features, everything pointed toward the same conclusion. Beneath Europa's frozen shell lies a global ocean, not a small ocean. Not a regional sea, an ocean that may contain more water than all of Earth's oceans combined. Imagine that for a moment. One of the largest bodies of liquid water in the solar system does not exist on Earth. It exists beneath kilometers of ice, orbiting Jupiter. The discovery transformed Europa from an interesting moon into one of the most important worlds in planetary science. Suddenly the conversation shifted. Scientists were no longer asking only geological questions. They began asking biological ones. Could life exist there? Nobody knows, at least not yet. But Europa possesses several ingredients associated with habitable environments: liquid water, chemical nutrients, energy sources generated through tidal heating. Those ingredients make it one of the most promising places to investigate. Even if Europa ultimately proves lifeless, the search itself will teach us an enormous amount about how habitable environments develop throughout the universe, and Europa is only the beginning. Travel farther outward through Jupiter's moon system and we arrive at Ganymede. At first glance, Ganymede appears less dramatic. There are no giant visible plumes, no spectacular volcanic eruptions, no thick atmosphere. Yet Ganymede is extraordinary in its own right. For one thing, it is the largest moon in the solar system. Larger than Mercury, larger than Pluto, large enough that many people are surprised it isn't classified as a planet. But size isn't its only distinction. Ganymede possesses its own magnetic field. That's exceptionally unusual for a moon. Generating a magnetic field requires internal complexity. Something interesting must be happening beneath the surface. Evidence suggests Ganymede contains enormous quantities of water hidden below layers of ice. In fact, some models indicate multiple ocean layers may exist. Rather than a single body of water, Ganymede's interior may resemble a stack of alternating ice and ocean layers. If true, the moon's internal structure is far more complicated than scientists once imagined. It's remarkable how often this happens. The deeper researchers look, the more complicated these worlds become. The same pattern appears again with Callisto. For many years, Callisto seemed like the least exciting member of Jupiter's major moon family. Io had volcanoes, Europa had its ocean, Ganymede had its magnetic field. Callisto appeared to be the quiet sibling. Yet evidence eventually suggested Callisto may also harbour a subsurface ocean, not necessarily as active or accessible as Europa's, but potentially present nonetheless. Once again, a seemingly simple ice-covered moon revealed hidden complexity. One begins to understand why planetary scientists become so enthusiastic about these worlds. Every time we think we've identified a frozen dead moon, another layer of the story emerges. Saturn's system offers even more examples. One of the most fascinating is Enceladus. We've already discussed its spectacular plumes when examining volcanic moons, but Enceladus deserves attention here as well because it perfectly illustrates how misleading appearances can be. Enceladus is relatively small. Its diameter is only about 500 kilometers. That's tiny compared to many major moons. For decades, nobody expected it to become one of the most important worlds in the solar system. Then the spacecraft Cassini-Huygens arrived. Near the South Pole, Cassini discovered enormous jets of water vapour erupting into space. These plumes were not minor features. They were direct evidence of ongoing activity. The implications were extraordinary. Liquid water existed beneath the surface. Further observations confirmed the presence of a global ocean. Today, Enceladus stands alongside Europa as one of the leading candidates in the search for extraterrestrial life. One reason is particularly compelling. The plumes effectively bring subsurface material into space. Future spacecraft may be able to sample that material directly. Instead of drilling through kilometers of ice, scientists can potentially fly through the plumes and analyze what comes out. Nature has provided a convenient shortcut. It's difficult not to appreciate the efficiency. Another remarkable ice moon is Saturn's Mimas. For many years, Mimas seemed straightforward. Its enormous Herschel crater dominates the landscape, giving the moon a superficial resemblance to a certain famous fictional space station. The comparison became impossible to ignore once people noticed it. Yet beneath the familiar jokes lies an intriguing mystery. Recent evidence suggests Mimas may contain a hidden ocean beneath its icy shell. If confirmed, this would dramatically alter our understanding of the moon. Scientists had long viewed Mimas as relatively inactive. Now it may join the growing list of worlds concealing liquid water beneath frozen exteriors. The lesson keeps repeating. Surface appearances can be deceiving. Farther outward, Uranus provides additional examples. Its major moons are often overshadowed by the more famous worlds orbiting Jupiter and Saturn, yet several show evidence of geological activity in their past. Ariel, in particular, displays enormous canyons and signs of resurfacing. These features suggest that internal processes once reshaped the moon. Whether subsurface oceans still exist today remains uncertain, but the geological record indicates a more active history than early observers imagined. Titania and Oberon may have experienced similar processes. Scientists continue studying these worlds because many questions remain unanswered. The farther we move from the Sun, the less detailed our observations become. Much of what we know about Uranus's moons comes from the brief flyby of the spacecraft Voyager 2 in 1986. Imagine trying to understand an entire world based on a single visit. There is still much left to discover. One particularly interesting aspect of ice moons is the role of tidal heating. We've encountered this process before with Io, but it affects icy worlds differently. Instead of generating vast quantities of molten rock, tidal heating can maintain liquid water beneath thick frozen crusts. The moon flexes slightly as gravity stretches and squeezes it. Heat is generated, ice melts, an ocean survives. Without tidal heating, many of these oceans would likely freeze solid. With it, they can persist for billions of years. That realization changed how scientists think about habitable environments. For much of history, the search for life focused heavily on distance from the sun. Too close and water evaporates. Too far and water freezes. Simple, or so it seemed. Ice moons complicated the picture. A world can exist far beyond the traditional habitable zone and still maintain liquid water internally. The source of energy doesn't have to be sunlight. Gravity can provide it. This dramatically expands the number of potentially interesting environments throughout the universe. Every giant planet may possess moons. Many of those moons may experience tidal heating. Some may contain subsurface oceans. The implications are enormous. Potentially habitable environments could be far more common than previously imagined. Of course, we should be careful. Liquid water does not automatically mean life. Scientists have not discovered extraterrestrial organisms on Europa, or Enceladus, or anywhere else. The question remains open, yet the possibility itself is enough to justify continued exploration. After all, some of the most important discoveries in history began with simple questions, and few questions are more important than whether life exists elsewhere. What's fascinating about ice moons is that they continually challenge our expectations. Cold worlds should be inactive, yet many are not. Frozen surfaces should indicate frozen interiors, yet many do not. Distance from the sun should reduce geological activity, yet gravity finds ways around that limitation. Again and again, these moons reveal complexity hidden beneath simplicity. A bright icy surface becomes a doorway to an ocean. A frozen crust conceals active geology. A distant moon becomes a potential habitat. The solar system keeps reminding us that appearances are not always reliable guides. Hundreds of years ago, if someone had suggested that some of the largest oceans in the solar system might exist not on planets, but on moons, the idea would have sounded absurd. After all, oceans require liquid water. Liquid water generally requires warmth, and many moons reside in some of the coldest regions of the solar system. Far from the sun, temperatures plunge so low that ice behaves more like stone than anything we encounter on Earth. The logic seems straightforward. Cold worlds should be frozen worlds. Case closed. Then spacecraft arrived. Measurements accumulated. Images returned. And scientists gradually realized they had been asking the wrong question. The crucial issue wasn't whether a moon's surface was frozen. The real question was what existed underneath. Because beneath those vast shells of ice, some moons appear to conceal oceans unlike anything found on Earth. Not lakes, not seas, entire global oceans, hidden worlds of liquid water stretching across entire moons. The discovery transformed planetary science. Suddenly, some of the most promising environments for life in the solar system weren't planets at all. They were icy moons, and among them, one world stands at the centre of the story: Europa. If Io is the celebrity of volcanic moons, Europa is the celebrity of ocean moons. Everything about it seems designed to attract scientific curiosity. Its surface is bright and relatively smooth. Long fractures stretch across the landscape. Ancient impact craters are surprisingly scarce. Those details immediately suggest something important. The surface is young. Something is renewing it. Something is reshaping it. Scientists first suspected an ocean beneath Europa decades ago, but the evidence became increasingly compelling as observations improved. The spacecraft Galileo provided some of the strongest clues. Measurements indicated that Europa likely possesses a salty ocean beneath its icy crust. Not a small ocean, a global one. Estimates vary, but many suggest Europa may contain more liquid water than all of Earth's oceans combined. That's a remarkable statement. Earth is often called the blue planet because of its vast oceans. Yet one distant moon orbiting Jupiter may contain even more water. The difference is location. On Earth, water sits on the surface. On Europa, water hides beneath ice. Scientists believe Europa's crust may be several kilometers thick, though exact values remain uncertain. Below that crust lies liquid water. Below the water lies rock, and that combination immediately attracts attention. Water interacting with rock creates chemistry. Chemistry creates possibilities. On Earth, some of the most fascinating ecosystems exist in deep oceans near hydrothermal vents. These environments receive no sunlight. Instead, life relies on chemical energy. The discovery revolutionized biology because it demonstrated that sunlight isn't always necessary. When scientists looked at Europa, An obvious question emerged. Could similar environments exist there? No one knows. But the possibility is intriguing enough that multiple missions have been designed specifically to investigate the Moon further. For decades, Europa has remained one of the most important targets in planetary science. Yet despite all the attention Europa receives, it is not alone. Far from it. In fact, one could argue that Saturn's moon Enceladus presents an equally compelling case. Enceladus is much smaller than Europa. Its diameter is only about 500 kilometers. By comparison, Europa measures over 3,100 kilometers across. For many years, Enceladus attracted relatively little attention. Then the spacecraft Cassini-Huygens changed everything. As Cassini studied the Moon, it discovered enormous plumes erupting from the South Polar region. Water vapor, ice particles, organic compounds. Material was literally being launched into space. The implications were extraordinary. Those plumes originated from an ocean hidden beneath the surface. For the first time, scientists weren't merely inferring the existence of a subsurface ocean, they were sampling material coming directly from it. Cassini flew through the plumes multiple times. Each pass provided additional information, and the findings kept becoming more exciting. The ocean appeared salty, chemical reactions appeared to be occurring at the seafloor, hydrogen was detected, organic molecules were present. The ingredients necessary for potentially habitable environments seemed increasingly abundant. Once again, it's important to remain careful. Scientists have not found life on Enceladus. No microbes, no fish, no alien squid organizing underwater civilizations. The evidence does not support those conclusions. What it does support is the existence of a remarkably promising environment, an ocean, energy, chemistry. Those factors make Enceladus one of the most compelling destinations in the solar system. What's especially remarkable is how accessible its ocean appears. Europa's ocean remains hidden beneath thick ice. Enceladus conveniently sprays samples into space. It's almost as though the Moon is helping researchers. Not intentionally, of course, but the effect is useful. Future missions may be able to analyze plume material in extraordinary detail without ever landing. Sometimes exploration gets lucky. Moving back to Jupiter, we encounter another potential ocean world, Ganymede, the largest moon in the solar system. For many years, Ganymede's size was its primary claim to fame. Then scientists began studying its interior more carefully. Evidence accumulated suggesting multiple layers of liquid water hidden beneath the surface. The structure may be surprisingly complex. Rather than containing one ocean, Ganymede may possess several. Imagine a layered interior. Ice, water, ice, water. Additional layers beneath. A planetary scale arrangement unlike anything found on Earth. The exact details remain uncertain, but one thing is clear. Ganymede is not simply a frozen rock drifting around Jupiter. Its interior appears dynamic and complicated. The Moon also possesses its own magnetic field, which further suggests internal activity. When people hear the phrase ocean world, they often imagine a relatively simple environment. The reality may be much stranger. Each ocean moon appears unique. Each possesses its own structure, its own history, its own geological processes. Callisto may belong to this family as well. For years, Callisto seemed like the quiet sibling among Jupiter's major moons. Its heavily cratered surface suggested a largely inactive world. Yet magnetic measurements indicate a subsurface ocean may exist there too. If so, Jupiter alone would host multiple ocean moons. That's an extraordinary realization. One planet, several worlds with hidden oceans. The implications extend far beyond the solar system. If Jupiter can host multiple ocean-bearing moons, perhaps giant planets elsewhere can do the same. The number of potential ocean environments throughout the galaxy could be enormous. And then there's Titan. Titan occupies a special position among ocean moons. because it combines multiple categories at once. We've already encountered Titan as an atmospheric moon. It possesses weather, clouds, rain, rivers, lakes. Yet beneath all of that, scientists believe another ocean exists, a vast subsurface ocean hidden beneath the icy crust. Titan effectively contains two different worlds. One visible, one concealed. The visible world features hydrocarbon lakes and methane weather systems. The hidden world may contain liquid water. Few objects in the solar system display such complexity. It's one reason Titan continues to attract enormous scientific interest. The moon feels less like a simple satellite, and more like a complete planetary system condensed into a single world. As researchers continued studying ocean moons, a fascinating pattern emerged. The oceans appeared in places where traditional expectations suggested they shouldn't exist, far from the sun, beneath thick ice, in environments previously assumed to be frozen solid. The explanation often comes back to tidal heating. We've encountered this process several times already because it keeps appearing throughout moon science, and for good reason. It is one of the most important energy sources in the outer solar system. As giant planets pull on their moons, the moons flex. The flexing generates heat. The heat melts ice. The oceans survive. Without tidal heating, many ocean moons would likely freeze completely. With it, they remain active for billions of years. The process effectively turns gravity into a power source. That's one of the reasons ocean moons transform discussions about habitability. Before these discoveries, scientists often focused on the traditional habitable zone around stars. The concept remains important. Yet ocean moons revealed another possibility. A world doesn't necessarily need strong sunlight. It needs energy. If gravity can provide that energy, liquid water becomes possible even far from the warmth of a star. That dramatically expands the range of environments worth studying. Some estimates suggest ocean worlds may actually be among the most common habitable environments in the universe. Not planets with surface oceans like Earth. Moons and planets with subsurface oceans hidden beneath ice. Think about how dramatically that changes the picture. For most of human history, oceans meant coastlines, waves, beaches, ships, the familiar relationship between water and sky. Ocean moons offer something completely different. Imagine spending your entire existence beneath a ceiling of ice. No sunlight, no stars, no visible horizon, only darkness and water stretching for immense distances. If life exists in such environments, its experience would be profoundly different from ours. Entire ecosystems could potentially evolve without ever seeing the sky. It's a strange idea. Yet nature has repeatedly demonstrated that it cares very little about our expectations. What once seemed impossible often becomes merely undiscovered, and ocean moons are among the best examples of that lesson. World after world keeps revealing hidden reservoirs beneath frozen exteriors: Europa, Enceladus, Ganymede, Callisto, Titan. Perhaps others yet to be confirmed. The list continues growing. Each discovery raises new questions. How many ocean worlds exist? How long have their oceans survived? What chemistry occurs within them? Could life emerge there? The answers remain uncertain, but the questions themselves are enough to drive exploration for decades. Because every hidden ocean represents an entire world we have barely begun to understand. When most people imagine a moon, they picture something that looks at least vaguely like our own. A rocky world. No air, no weather, no clouds drifting overhead, no rain, no seasons worth discussing. Just a silent landscape exposed directly to space. For a long time that seemed like a reasonable expectation. After all, the moon has no substantial atmosphere. Mercury has almost none. Many smaller worlds throughout the solar system are essentially bare surfaces sitting beneath a black sky. Then astronomers discovered that some moons had entirely different plans. Instead of existing as airless rocks or icy spheres, They developed atmospheres, not thin traces of gas, not barely detectable wisps. Actual atmospheres, some with clouds, some with weather, some with winds, some with seasonal changes, and in one remarkable case, an atmosphere so thick that a person standing on the surface would feel more air pressure than they do on Earth. These worlds blur the line between moons and planets. They remind us that nature rarely respects the categories humans invent, and no atmospheric moon is more famous than Titan. Orbiting Saturn more than 1 billion kilometers from the Sun, Titan is the second largest moon in the solar system. Only Ganymede is larger, yet size alone isn't what makes Titan extraordinary. Its atmosphere does. Before spacecraft visited Saturn, Titan appeared mysterious. Telescopes revealed little more than an orange haze surrounding the moon. Unlike most moons whose surfaces could be observed directly, Titan hid everything beneath thick clouds and smog-like layers. For decades, nobody knew exactly what was underneath. It was as if the moon had deliberately wrapped itself in a blanket and refused to cooperate. Scientists became increasingly curious. What was hiding below? Mountains? Ice? Oceans? Something stranger? The answer began arriving with missions such as Cassini-Huygens. As observations improved, Titan transformed from a mystery into one of the most fascinating worlds ever discovered. Its atmosphere turned out to be denser than Earth's. Think about that for a moment. A moon, not a planet, a moon, possessing an atmosphere with greater surface pressure than the world you are currently sitting on. That fact alone would make Titan remarkable. Yet it gets even better. Titan has weather, real weather. Clouds form, rain falls, winds blow, seasons change, rivers carve landscapes, lakes collect in low-lying regions, entire weather systems operate across the moon. If that description sounds suspiciously Earth-like, you're not alone. Planetary scientists often compare Titan to a strangely modified version of Earth. The similarities are obvious, the differences are enormous. On Earth, water drives the weather cycle. Water evaporates, clouds form, rain falls, rivers flow. On Titan, methane and ethane perform those roles instead. The moon is so cold that substances which exist as gases on Earth become liquids there. Imagine standing beside a lake not of water, but of liquid methane. Imagine watching methane rain fall from methane clouds. Imagine rivers carrying hydrocarbons across the landscape. That is everyday weather on Titan. If you could somehow stand safely on its surface, the environment would feel both familiar and deeply alien. You would recognize clouds, you would recognize rain, you would recognize coastlines. Yet almost every substance involved would differ from what you're used to. It's one of the closest things in the solar system to an alternative version of Earth. The atmosphere itself consists primarily of nitrogen, much like Earth's atmosphere. Again, another surprising similarity. Scientists suspect Titan may preserve clues about chemical processes that occurred on the young Earth before life emerged. For that reason alone, it remains one of the most important destinations in planetary science. Future missions are already being planned. Researchers know there is still much to learn. The deeper they investigate Titan, the more interesting it becomes. Yet Titan isn't the only moon with an atmosphere. Far from it. Let's travel outward to Neptune's largest moon, Triton. We've already encountered Triton several times during our journey. It was captured. It possesses active geology, and it also has an atmosphere. At first glance, that might seem surprising. Triton is incredibly cold. Temperatures are among the lowest measured in the solar system, yet even here, nature finds a way. Triton's atmosphere is extremely thin compared to Titan's, but it exists. Primarily composed of nitrogen, with smaller amounts of methane and carbon monoxide, the atmosphere changes as sunlight warms parts of the surface. Frozen nitrogen can sublimate directly into gas. The process resembles dry ice evaporating on Earth. As conditions change, the atmosphere responds. Seasonal variations occur, pressure changes occur, even weather-like processes may take place. The Voyager 2 spacecraft observed dark plumes rising above Triton's surface in 1989. These features may have been driven by sunlight heating material beneath translucent layers of ice. The resulting eruptions created dramatic streaks across the landscape. For a world so far from the Sun, Triton remains surprisingly dynamic. Its atmosphere is not thick. It does not produce methane rain like Titan. Yet its existence reminds us that atmospheres can emerge in unexpected places. Sometimes only a small amount of gas is necessary to create interesting phenomena. Pluto provides another useful comparison. Technically not a moon, of course, but it shares many characteristics with Triton. In fact, scientists suspect Triton may once have resembled Pluto before Neptune captured it. Both possess nitrogen-rich surfaces, both support thin atmospheres, both exist in the cold outer reaches of the solar system. Studying one helps researchers understand the other. The connection highlights how atmospheric processes operate even at extraordinary distances from the Sun. Then there is Io. At first glance, Io seems like an unlikely candidate for this discussion. When people think about atmospheres, they imagine clouds and weather. Io offers something different. Its atmosphere is extremely thin and highly variable. Volcanic eruptions continuously release sulfur dioxide gas. Some of that gas forms a temporary atmosphere around the Moon. As temperatures change, portions of the atmosphere collapse back onto the surface. Then volcanic activity replenishes it. The result is an environment unlike any other. Io's atmosphere exists in a delicate balance between volcanism, sunlight, and freezing temperatures. It's not a pleasant place. It isn't particularly stable. Yet it demonstrates another way atmospheres can arise. Sometimes geology supplies the necessary gases. The Moon essentially breathes through its volcanoes. Even Europa may possess an atmosphere, though calling it an atmosphere in the traditional sense requires some caution. The Moon's icy surface is constantly bombarded by charged particles trapped within Jupiter's magnetic field. Those interactions break apart molecules. Tiny quantities of oxygen accumulate. The resulting atmosphere is extraordinarily thin. A human would never notice it. Yet scientifically, it matters. It reveals how interactions between radiation and ice can gradually generate atmospheric components. Again, the process differs from Titan. Different worlds find different solutions. One of the fascinating things about atmospheric moons is how they challenge assumptions regarding size. Conventional wisdom suggests that small worlds struggle to retain atmospheres, and that's generally true. Gravity helps hold gases in place. Larger worlds tend to do this more effectively. Yet atmospheric moons demonstrate that the situation is more nuanced. Temperature matters, composition matters, distance from the Sun matters, geological activity matters. Multiple factors work together. Titan's atmosphere survives partly because the Moon is relatively massive and extremely cold. Cold temperatures reduce the tendency of gases to escape. Triton's atmosphere survives through seasonal cycles involving frozen nitrogen. Io continuously replenishes its atmosphere through volcanism. Different mechanisms produce different outcomes. The diversity is remarkable, and it has important implications beyond our solar system. Today, astronomers routinely discover planets orbiting distant stars. Many of those planets are giant worlds. If giant planets exist elsewhere, moons may exist around them as well. Some of those moons could potentially possess atmospheres, perhaps thick atmospheres, perhaps weather systems, perhaps environments even more exotic than Titan. The possibility excites researchers because atmospheric moons expand the range of potentially interesting worlds. A moon doesn't have to resemble our own moon. It can possess clouds, rain, winds, climate cycles. The distinction between moon and planet begins to feel less important than the actual characteristics of the world itself. That's one reason Titan receives so much attention. It forces us to rethink familiar categories. Technically, it's a moon. Functionally, in many respects, it behaves more like a planet. And the universe appears perfectly comfortable with that arrangement. As we continue exploring moon types, a broader pattern becomes clear. Moons are not simply smaller versions of planets. Some are volcanic, some are icy, some contain oceans, some possess atmospheres, some combine multiple categories at once. The diversity is extraordinary. Consider for a moment how unusual Earth actually is. Our planet is active. Mountains rise, volcanoes erupt, rivers reshape landscapes. Wind, rain, ice, and oceans constantly modify the surface. If a crater forms, nature eventually begins erasing it. Given enough time, entire geological chapters can disappear. Now imagine the opposite. Imagine a world where almost nothing changes. A world so quiet that scars inflicted billions of years ago remain visible today. A world that remembers nearly everything that has happened to it. Those are the cratered rocky moons. Unlike volcanic moons that continually rebuild themselves or ocean moons that conceal dynamic interiors beneath ice, these worlds often seem frozen in time. Not literally frozen, although many are cold, but geologically frozen. Their surfaces preserve records stretching back toward the earliest days of the solar system. Every impact, every collision, every ancient bombardment, written directly into stone. In many ways, these moons function as historical archives. They are not exciting because of what is happening today. They are exciting because of what happened billions of years ago and never got erased. Some of the oldest surviving landscapes in the solar system belong to this family, and among the most famous examples is our own moon. It's easy to forget just how heavily cratered the moon actually is. Most people notice the dark regions first. The Maria, those broad volcanic plains visible even to the naked eye. Yet look more carefully and an entirely different story emerges. Crater after crater, large ones, small ones, ancient ones, young ones. Some overlap each other, some stretch for hundreds of kilometers. The moon's surface resembles a geological scrapbook assembled over billions of years. Unlike Earth, the moon lacks substantial atmosphere. There is no rain, no rivers, no wind erosion, no oceans. Consequently, impacts remain preserved for extraordinary lengths of time. When an asteroid struck the moon 3 billion years ago, the resulting crater often remained visible. When another impact occurred 2 billion years ago, it remained visible too. The same is true for countless other collisions. The result is a world that preserves an almost uninterrupted record of solar system history. Scientists treasure this record. By studying lunar craters, researchers reconstruct the era known as the Late Heavy Bombardment, a period when impacts were far more common than they are today. Some estimates suggest enormous numbers of asteroids and comets bombarded the inner solar system during that time. Earth experienced those impacts too. Unfortunately for historians, Earth subsequently covered most of the evidence with plate tectonics, erosion, and geological activity. The moon did not. It kept the receipts. One particularly famous example is Tycho crater. Even amateur astronomers can spot it. Bright rays of ejected material spread across the lunar surface like spokes from a wheel. The impact that created Tycho occurred relatively recently in geological terms, roughly 108 million years ago. That may sound ancient. For planetary geology, it's practically yesterday. Then there's Copernicus crater, another magnificent feature, roughly 93 kilometers across. Visible through modest telescopes, its central peaks and terraced walls provide clues about how enormous impacts reshape planetary surfaces. In many respects, the moon serves as the textbook example of a cratered rocky world. Yet it is hardly alone. Travel outward to Mars and we encounter 2 moons that fit this category beautifully, Phobos and Deimos. We've already discussed them as possible captured moons, but they deserve attention here for another reason. Both are heavily cratered, particularly Phobos. The most striking feature on Phobos is Stickney crater. Named after the maiden name of the wife of the astronomer Asaph Hall, who discovered the moon, Stickney dominates the landscape. The crater measures roughly 9 kilometres across. That may not sound enormous until you remember that Phobos itself is only about 22 kilometres wide. Imagine a crater nearly half the width of the entire moon. It's as though a single impact almost destroyed the world. In fact, scientists believe the collision came astonishingly close to doing exactly that. Gigantic grooves stretch away from Stickney across the surface. For years, researchers debated their origin. Were they fractures created by the impact? Were they produced by tidal stresses from Mars? The discussion continues. Whatever the explanation, Phobos wears its history openly. Its battered appearance tells the story of a small object surviving in a dangerous environment. Deimos appears somewhat gentler by comparison. Its craters are softened by loose surface material known as regolith. Over time, impacts have pulverized rock into fine debris that partially fills older craters. The result is a smoother appearance than Phobos, yet Deimos remains fundamentally a cratered world. Another ancient survivor, another record keeper. Moving outward to Saturn's system introduces us to Mimas. Mimas is perhaps the most recognizable cratered moon in the solar system, not because of its scientific importance, although it certainly has plenty, not because of its size, rather because one crater dominates the moon so completely that it became famous. Herschel Crater. The feature is enormous, approximately 130 kilometers across. Given that Mimas itself measures only about 396 kilometers in diameter, the crater occupies a huge fraction of the moon. The impact nearly shattered the entire world. If the collision had been slightly more energetic, Mimas might not exist today. Instead, it survived. Barely. The resulting crater creates one of the most distinctive appearances in planetary science. It's difficult to look at Mimas and not immediately notice it. Scientists naturally focus on the geology. The public often notices the resemblance to a certain fictional battle station. Both observations are understandable. Beyond Herschel, Mimas preserves a heavily cratered landscape that reveals its great age. Unlike active moons such as Io, Mimas has undergone relatively little resurfacing. Ancient impacts remain visible across vast regions. The moon functions as another historical archive, another witness to the violent early solar system. Saturn offers additional examples. Hyperion, despite its chaotic rotation, also belongs partly within this category. Its surface is covered with deep craters and strange cavities. The moon resembles a giant sponge drifting through space. Many of its craters have unusually dark floors. Scientists believe organic rich material accumulates within them. The appearance is unlike almost anything else in the solar system. Hyperion demonstrates an important lesson. Even heavily cratered worlds can be unique. The basic process may be familiar. Impacts occur, craters form, history accumulates, yet local conditions create distinctive results. No two cratered moons look exactly alike. Then there is Phoebe, previously introduced as a captured moon of Saturn. Phoebe's surface is saturated with impact scars. Large craters dominate much of the landscape. The moon's dark coloration suggests material composition quite different from Saturn's regular icy satellites. Studying Phoebe provides insights not only into impacts, but also into the populations of objects that existed in the outer solar system billions of years ago. Its surface acts like a geological time capsule. Every crater contributes information. Every impact preserves evidence. Together they create a record stretching back toward the solar system's earliest periods. Farther outward still, we arrive at one of the greatest collections of cratered moons anywhere, the major moons of Uranus, Oberon, Umbriel, and portions of Titania. These worlds are ancient, cold, and heavily scarred. Umbriel in particular presents an extraordinarily old surface. Impact craters cover much of the moon. Unlike more active worlds, geological processes have done relatively little to erase them. One famous feature, known as Wunder Crater, stands out because of a bright ring surrounding it. Against Umbriel's dark surface, the contrast is striking. Scientists continue investigating exactly why the material appears brighter. Even seemingly simple craters can contain mysteries. Oberon tells a similar story. Its surface preserves countless impacts accumulated over immense spans of time. Some craters display bright ejecta deposits. Others reveal evidence of ancient geological activity. Though largely inactive today, Oberon clearly experienced a more complicated history than its current appearance might suggest. One fascinating aspect of cratered moons is how scientists use them as clocks. Not literal clocks, of course, geological clocks. The principle is surprisingly simple. Older surfaces accumulate more craters, younger surfaces accumulate fewer. If one region contains thousands of impacts while another contains only a handful, the second region is probably younger. This technique allows researchers to estimate relative ages across planetary landscapes. It's not perfect, but it is extraordinarily useful. In many cases, crater counting provides the best available method for reconstructing geological history. The approach has been applied throughout the solar system, on moons, on planets, on asteroids. Again and again, impacts become tools for understanding time. Without craters, much of planetary science would be far more difficult. Ironically, destruction creates information. Each collision leaves behind evidence. Each crater becomes a data point. Each scar helps reconstruct ancient events. Another fascinating reality is that many cratered moons survived impacts that should arguably have destroyed them. The early solar system was not a peaceful place. Large objects collided frequently. Some worlds were shattered, some merged, some disappeared entirely. The cratered moons we observe today are survivors. Their surfaces preserve evidence of battles they somehow endured. Mimas survived Herschel. Phobos survived Stickney. Countless other moons survived impacts whose energies are difficult to imagine. The fact that these worlds still exist at all is remarkable. They're veterans of an extraordinarily violent era, yet despite their battered appearances, cratered moons should not be mistaken for boring worlds. Quite the opposite. Their apparent simplicity often conceals tremendous scientific value. A volcanic moon tells us about ongoing activity. A cratered moon tells us about ancient history. Both are important. In fact, without cratered worlds, our understanding of solar system evolution would be dramatically poorer. They preserve records erased elsewhere. They remember events forgotten by more active worlds. They function as archives written in stone. Long before astronomers discovered thousands of planets beyond our solar system, there was a widespread assumption that the outer regions beyond Neptune were mostly empty. A few icy objects, perhaps, some scattered debris, nothing especially complicated. The giant planets dominated attention, while the distant frontier remained largely mysterious. Then better telescopes arrived. More surveys were conducted, new worlds were discovered, and gradually a very different picture emerged. The outer solar system turned out to be crowded. Not crowded by everyday standards, of course. Space remains overwhelmingly empty. But compared to earlier expectations, the distant regions beyond Neptune contain a remarkable population of icy worlds. Some are tiny, some are surprisingly large, and several possess moons of their own. This realization changed how scientists viewed dwarf planets. Rather than isolated objects drifting alone through darkness, many turned out to be members of miniature systems complete with companion moons. These moons may not be as famous as Titan or Europa, but they tell an important story. They reveal that moon formation isn't restricted to giant planets. Even relatively small worlds can acquire satellites. Even at the edge of the solar system, even in environments where sunlight is little more than a bright star. Perhaps the most famous example is Pluto and Charon. For much of the 20th century, Pluto occupied a special place in astronomy. Discovered in 1930 by Clyde Tombaugh, it was celebrated as the 9th planet. generations of students memorized its position in the solar system. Then, as additional discoveries accumulated, astronomers realized Pluto belonged to a much larger population of distant icy objects. Eventually it was reclassified as a dwarf planet. The change generated endless debates. What received less attention was the extraordinary nature of Pluto's moon system. Charon is enormous compared to Pluto, remarkably enormous. Most moons are tiny relative to the worlds they orbit. Charon is different. Its diameter is more than half that of Pluto. The two objects are so closely matched that some astronomers describe them as a double dwarf planet system. In fact, the centre of mass around which they orbit lies outside Pluto itself. That's highly unusual. Imagine a dance where neither partner truly leads. Instead, both move around a shared point in space. That's essentially what Pluto and Charon do. The relationship is unlike anything seen between Earth and the Moon, or Jupiter and its satellites, or Saturn and Titan. Pluto and Charon are closer to equals. For billions of years they have remained locked together, showing the same faces toward one another continuously. If you stood on Pluto, Charon would hang motionless in the sky. It would not rise, it would not set, it would simply remain there, forever watching. Meanwhile, if you stood on Charon, Pluto would do exactly the same. The arrangement creates one of the most remarkable gravitational partnerships in the solar system, yet Charon is not alone. Pluto possesses 4 additional moons: Nix, Hydra, Kerberos, and Styx. These smaller companions orbit farther out, creating a surprisingly complex system around a world once thought to be lonely. The discovery of these moons transformed Pluto from a single, distant object into an entire miniature planetary system. And the more scientists studied it, the stranger it became. The spacecraft New Horizons revealed astonishing diversity. Towering mountains, frozen plains, complex geology, unexpected activity. Even at the edge of the solar system, nature remained creative. Charon itself possesses enormous canyons, fractured terrain, and evidence of ancient internal processes. Far from being a simple chunk of ice, it turned out to be a fascinating world in its own right. Pluto's system also provided clues about moon formation. Many researchers believe Charon formed after a giant collision, somewhat similar to the process that may have created Earth's moon. A massive impact ejected material into orbit. That material eventually assembled into Charon and possibly the smaller moons as well. If correct, then Pluto's family began with a catastrophic event, a familiar theme throughout moon science. Again and again, collisions shape destinies. Moving farther through the Kuiper belt brings us to another dwarf planet, Haumea. Haumea is one of the strangest objects in the solar system. Its rapid rotation has stretched it into an elongated shape resembling a cosmic rugby ball. Most large worlds become roughly spherical because gravity pulls material evenly in all directions. Haumea spins so quickly that it never fully achieved that appearance. The result is extraordinary. Orbiting Haumea are 2 known moons, Hiiaka and Namaka. Both are thought to be fragments associated with an ancient collision. Evidence suggests Haumea belongs to an entire family of objects produced by a massive impact long ago. Imagine an enormous crash scattering material throughout the outer solar system. Some fragments become independent objects, others remain nearby as moons. The event effectively created a celestial family tree. Studying Haumea and its moons allows scientists to investigate how collisions operate in extremely distant environments. Even billions of kilometers from the Sun, impacts remain capable of reshaping entire systems. Then there is Eris. For a time, Eris became famous for a reason completely unrelated to its moon. Its discovery helped trigger the debate that ultimately led to Pluto's reclassification. Eris turned out to be similar in size to Pluto, forcing astronomers to confront an uncomfortable question. If Pluto was a planet, should Eris be one too? The discussion eventually led to the dwarf planet category, yet Eris possesses a moon of its own, Dysnomia. Compared to Charon, Dysnomia is relatively modest. Nevertheless, its importance cannot be overstated. The moon allowed scientists to calculate Eris's mass accurately. By observing Dysnomia's orbit, researchers could determine the gravitational pull of Eris itself. This is one of the hidden benefits of moons. They often reveal information about their parent worlds. Without Dysnomia, understanding Eris would have been much more difficult. Makemake provides another example. For years, Makemake appeared moonless. Then observations revealed a small companion, officially designated S/2015 136472, 1 and later nicknamed MK2. The moon helped explain several mysteries involving the dwarf planet. Again, a companion transformed scientific understanding. Even tiny moons can have enormous importance. One lesson becomes increasingly obvious when examining dwarf planet moons. Complexity is not reserved for large worlds. The giant planets possess spectacular systems, certainly, yet even distant dwarf planets can host fascinating companions. The solar system seems remarkably willing to create moons whenever circumstances allow. Size helps, gravity helps. But neither is absolutely required. Given enough time and the right conditions, companions emerge, and while these moons occupy some of the smallest planetary systems known, the next group occupies the opposite extreme. These are moons so large that calling them moons almost feels unfair. Worlds that rival planets, worlds larger than Mercury, worlds with oceans, atmospheres, magnetic fields, and geological histories. Objects that force us to confront a simple question: what really separates a moon from a planet? The answer, surprisingly, is often just what it happens to orbit. The largest moon in the solar system is Ganymede. Orbiting Jupiter, Ganymede stretches roughly 5,268 kilometers across. To appreciate that number, consider this. Mercury's diameter is approximately 4,879 kilometers. Ganymede is larger. If Jupiter suddenly disappeared and Ganymede found itself orbiting the Sun independently, many people would instinctively call it a planet. Nothing about its physical characteristics would seem out of place. It has a differentiated interior, a magnetic field, evidence for subsurface oceans, complex geology. The only reason it remains classified as a moon is because it orbits Jupiter. That's it. The distinction is surprisingly simple, and Ganymede is not alone. Titan, Saturn's largest moon, is nearly as large. With a diameter of about 5,150 kilometers, Titan also exceeds Mercury in size. Once again, if it orbited the Sun directly, it would almost certainly be considered a planet. Yet Titan goes even further. Unlike Mercury, Titan possesses a thick atmosphere. In fact, its atmosphere is denser than Earth's. Clouds drift through its skies, rain falls, rivers flow, lakes collect, entire weather systems operate. Imagine explaining that to an astronomer from the 19th century. A moon larger than Mercury, with a dense atmosphere and active weather. The response would likely involve considerable disbelief, yet Titan exists. And it continues challenging assumptions. Callisto belongs in this category as well. Although slightly smaller than Mercury, it remains immense. Its surface preserves billions of years of history. Its interior may contain an ocean. Its sheer size places it among the largest moons ever discovered. Europa, while smaller, remains substantial enough to qualify as a major world in its own right. The same is true for Earth's moon. Although not larger than Mercury, it is unusually large relative to its parent planet. The Earth-Moon system remains one of the most balanced planet-moon pairings in the solar system. Then there is Triton. Captured by Neptune long ago, Triton is large enough to qualify as a major planetary body. If it remained in the Kuiper belt today, it might be classified alongside Pluto and other dwarf planets. Instead, Neptune claimed it. The result is one of the largest captured moons known. These giant moons reveal something important. The distinction between planets and moons is often historical rather than physical. Many moons possess characteristics we normally associate with planets: atmospheres, oceans, magnetic fields, complex geology, weather, active surfaces. The universe does not seem particularly concerned with maintaining neat categories. A giant moon can be every bit as interesting as a planet, sometimes more interesting. And as astronomers continue searching around other stars, this lesson becomes increasingly relevant. Some exomoons may eventually prove larger than Mars, perhaps larger than Earth. The line between moon and planet may become even blurrier. For now, however, the giant moons of our solar system already demonstrate the principle beautifully. A world does not need planetary status to be extraordinary. Sometimes all it needs is size, complexity, and a few billion years to evolve. By this point in our journey, we've encountered moons that formed alongside their planets, moons that were captured from elsewhere, moons that hide oceans, generate volcanoes, sculpt rings, and even produce weather. Despite all their diversity, most of those systems share a familiar pattern. One object clearly dominates. The planet is larger. The planet contains most of the mass. The moon circles around it. Simple, at least most of the time. But nature occasionally creates systems that refuse to fit neatly into that arrangement. Sometimes a moon becomes so large relative to its parent world that the distinction between leader and follower begins to blur. Instead of a giant planet with a small companion, you end up with two substantial worlds locked together in a gravitational partnership. These are often called double worlds. The term is not an official classification recognized everywhere in astronomy, but it captures the basic idea beautifully. Neither object feels entirely subordinate. Neither object completely dominates. The pair behaves more like partners than a traditional planet and moon system, and nowhere is this more obvious than Pluto and Charon. If there is a celebrity among double-world candidates, Charon holds the title. We've already visited Pluto's moon system while discussing dwarf planet moons, but Charon deserves a much closer look because it fundamentally challenges how we think about moons. Charon is huge compared to Pluto. Not merely large, huge. Its diameter measures roughly 1,212 kilometers, while Pluto itself is about 2,377 kilometers across. That means Charon is more than half the size of Pluto. To appreciate how unusual this is, consider our own moon. Earth's moon is large compared to its parent planet, but Earth is still substantially larger. The imbalance remains obvious. Pluto and Charon are different. The two worlds appear almost like siblings, and the most important detail isn't their size. It's their center of mass. Normally, when a moon orbits a planet, both objects technically orbit a common center of mass called the barycenter. However, that point usually lies deep inside the larger object. Earth and the Moon do this. Jupiter and Ganymede do this. Saturn and Titan do this. The barycenter remains inside the planet. Pluto and Charon break the rule. Their barycenter lies outside Pluto entirely. Imagine two ice skaters spinning around one another while holding hands. Instead of one standing nearly still while the other circles around, both move significantly. That's essentially what Pluto and Charon do. Neither object remains fixed. Both orbit a point in space located between them. This arrangement makes the system feel fundamentally different. Some astronomers have argued that Pluto and Charon should be considered a binary dwarf planet system, rather than a traditional planet and moon pair. The debate remains ongoing, but the reasoning is understandable. The relationship simply doesn't resemble most moon systems. There's another fascinating consequence. Pluto and Charon are tidally locked to each other. Not merely one-way tidal locking like Earth and the Moon, mutual tidal locking. Each world always shows the same face to the other. If you stood on Pluto, Charon would remain fixed in the sky. Forever. It would never rise, never set, never drift across the heavens. It would simply hang there, day after day, year after year, million after million years. Likewise, if you stood on Charon, Pluto would remain permanently suspended in the same location overhead. It's one of the strangest sky views in the solar system. The arrangement feels almost engineered. Yet gravity achieved it naturally. The longer scientists studied Pluto and Charon, the more interesting the system became. The spacecraft New Horizons revealed two surprisingly complex worlds. Pluto displayed glaciers, mountains, nitrogen ice plains, and signs of ongoing geological activity. Charon exhibited enormous canyons stretching across vast distances. Neither looked like a simple frozen rock. Both possessed rich histories. Both evolved independently. Both deserved attention as worlds in their own right. That's one of the defining characteristics of double-world candidates. The moon stops feeling like an accessory. Instead, it becomes a destination, a place with its own geological story, its own evolution, its own identity. Pluto and Charon are perhaps the clearest example, but they are not the only system that pushes us in this direction. Earth and the Moon occupy an interesting middle ground. Technically, Earth and the Moon do not qualify as a true double-world system under the barycenter definition, because the centre of mass remains inside Earth. Yet compared to most planet-moon pairs, our system is remarkably balanced. The Moon's diameter is more than 1/4 that of Earth. For a major moon, that's enormous. Many moons are tiny compared to their planets. The Moon is not. Its influence on Earth is substantial. It drives tides. It helps stabilise Earth's axial tilt. It has shaped human culture for thousands of years. Some researchers have even argued that the Moon contributed to environmental stability that benefited the development of complex life. Whether or not every detail of that argument proves correct, the Moon's importance is undeniable. Earth would be a different world without it. The relationship is unusually intimate. When viewed from space, Earth and the Moon often appear less like a planet dragging around a satellite and more like two worlds travelling together. In fact, astronauts repeatedly commented on this impression during the Apollo era. The Moon wasn't a distant speck. It was a neighbouring world, close enough to visit, large enough to dominate the sky, significant enough to influence Earth's future. If Charon represents the strongest double-world candidate, Earth's moon might represent the strongest near miss. Then there is Triton. Not because it currently forms a double-world system with Neptune, but because of what it may once have been. Many scientists suspect Triton originated in the Kuiper Belt as an independent dwarf planet. Before Neptune captured it, Triton may have possessed its own identity entirely separate from the giant planet. Some models even suggest Triton could have been part of a binary system. Imagine that for a moment. A world that may once have participated in a double-world partnership before Neptune intervened and completely altered its future. The solar system's history becomes much more dynamic when viewed through this lens. Partnerships form, systems break apart, worlds get captured, relationships change, nothing remains entirely fixed. The possibility of double worlds becomes even more interesting when we consider discoveries beyond our solar system. Today, astronomers routinely identify planets orbiting distant stars. Many of those planets are giant worlds. And if giant worlds exist, moons may exist too. Some theoretical studies suggest certain exomoons could be extraordinarily large, potentially Mars-sized, perhaps even Earth-sized under exceptional circumstances. Now imagine an Earth-sized moon orbiting a Neptune-sized planet, or two nearly equal-sized bodies locked together in a mutual gravitational dance. Such systems could easily blur the distinction between planet and moon. Future discoveries may force astronomers to rethink existing definitions. Again, astronomy has a long tradition of doing that. Every few decades, observations reveal something unexpected. Categories that once seemed obvious become less certain. Definitions evolve. Double worlds sit directly in that grey area. They remind us that nature operates along continuums rather than sharp boundaries. One reason scientists find these systems so valuable is that they reveal how arbitrary some classifications can be. Consider Ganymede. It's larger than Mercury. Titan is larger than Mercury too, yet neither is called a planet. Mercury is. Why? Because Mercury orbits the Sun directly. Meanwhile, Ganymede and Titan orbit planets. The distinction has little to do with their physical characteristics. It depends largely on orbital relationships. Double-world systems push that logic to its limits. When two bodies become similar enough, deciding which is primary starts feeling less meaningful. The relationship itself becomes the interesting feature. Nature seems perfectly comfortable creating such arrangements. And there may be advantages. Large companion worlds can influence one another strongly. Tidal interactions become important. Rotational behaviour changes. Geological histories become intertwined. What happens on one world can affect the other. Pluto and Charon provide an excellent example. Their mutual tidal locking evolved because both objects continuously exchanged energy through gravitational interactions. Over immense spans of time, the system settled into its current configuration. The result is extraordinarily stable, a partnership maintained for billions of years. There is something appealing about that image, not in a sentimental sense, in a scientific one. Two worlds forming together, evolving together, and remaining connected across geological time. The solar system contains many relationships between planets and moons. Few are as balanced as this, and balance appears repeatedly whenever scientists discuss potential double worlds. It's not merely about size, it's about influence, mutual influence. When one body begins affecting the other nearly as much as it is affected in return, the traditional hierarchy starts weakening. The distinction between planet and moon becomes less obvious. Pluto and Charon demonstrate this beautifully. Neither object completely dominates. Both matter. Both contribute. Both help define the system. As our ability to discover distant worlds improves, we may eventually find even more extreme examples, perhaps binary dwarf planets, perhaps Earth-sized moon systems, perhaps arrangements unlike anything currently known. The universe has a habit of being more imaginative than expected. For now, however, double worlds occupy a fascinating middle ground. Not quite traditional planet-moon systems, not quite equal planetary pairs, something in between. By now, we've explored moons that formed with planets, moons that were captured, moons that sculpt rings, moons that hide oceans, moons with atmospheres, moons that rival planets in size, and even systems where the distinction between moon and planet begins to blur. Yet the final category of moon before we step back and consider the bigger picture may be the most mind-bending of all. Because these are moons that push beyond the familiar architecture of our solar system. Some may no longer orbit planets at all. Others circle worlds around stars so distant that we can barely detect the planets themselves. Some remain hypothetical, some are supported by growing evidence, and all of them force us to ask a fascinating question. What happens to a moon when its home changes, or disappears entirely? Let's begin with rogue moons. At first, the idea sounds almost contradictory. A moon, by definition, orbits a planet. Remove the planet and surely it stops being a moon. Problem solved. Except nature is rarely that simple. Imagine a young planetary system billions of years ago. Multiple giant planets are forming. Countless smaller worlds are moving through space. Gravitational encounters occur constantly. Some are gentle, others are catastrophic. Over time, planets migrate. Orbits shift. Entire worlds get thrown onto new trajectories. Modern astronomy increasingly suggests that planetary systems can be surprisingly chaotic during their youth. In some cases, planets may even be ejected completely. A giant planet that once orbited a star can be flung into interstellar space, through gravitational interactions with neighbouring worlds. Such planets are called rogue planets. They wander the galaxy without a parent star, and that naturally raises another question. What happens if a rogue planet already has moons? The answer is remarkable. The moons may come with it. Instead of remaining behind, some satellites could continue orbiting their planet as both objects travel through the darkness between stars. Imagine such a system. No sunrise, no sunset, no bright star dominating the sky. Only the faint glow of distant suns scattered across the galaxy. A lonely planet drifting through interstellar space. And around it, one or more moons continuing their endless orbits. In that scenario, the moons are technically still moons. Their planet remains. Their star does not. The image feels almost surreal. Yet computer simulations suggest it is entirely possible. Some studies indicate that moons can remain gravitationally bound to planets even during violent ejection events. The exact survival rate remains uncertain. Many moons would likely be lost. Others might endure. If so, there may be countless rogue moons travelling through the Milky Way right now. Most would be impossible to detect with current technology. They would be dark, cold, distant, almost invisible, yet their existence remains plausible. The thought is strangely compelling. A moon that has never seen a sunrise for billions of years. A world illuminated only by starlight and whatever heat its parent planet provides. It sounds like science fiction. Increasingly, it sounds like astronomy. And things become even more interesting when we consider tidal heating. We've encountered tidal heating repeatedly throughout this journey because it is one of the most important energy sources available to moons. If a rogue planet retained a large moon, gravitational interactions could continue generating heat. That means subsurface oceans might survive even without a nearby star. Think about that. A moon drifting between stars. A frozen surface exposed to deep space. Yet beneath the ice, a liquid ocean could persist, potentially for immense periods of time. The implications are extraordinary. For generations, scientists assumed habitable environments required sunlight. Ocean moons have already complicated that assumption. Rogue moon systems complicate it even further. Life, if it exists elsewhere, may not care nearly as much about starlight as humans do. Energy can come from other sources. Gravity remains one of the most important. Some researchers have even explored the possibility that rogue planets with large moons could maintain surprisingly stable environments beneath thick atmospheres or ice layers. No one knows how common such systems might be, but the possibility alone expands our understanding of where interesting worlds might exist. The galaxy suddenly feels much larger, and much stranger. Of course, rogue moons are difficult to observe. Exomoons present a different challenge. An exomoon is exactly what the name suggests. A moon orbiting an exoplanet. An exoplanet, in turn, is a planet orbiting another star. Today, astronomers have confirmed thousands of exoplanets. Some are giant gas worlds larger than Jupiter. Some resemble Neptune. Some are rocky planets. Some occupy habitable zones. Others orbit scorchingly close to their stars. The diversity is astonishing. Given how common moons are in our own solar system, one conclusion seems unavoidable. Many exoplanets should have moons, perhaps most of them. After all, Jupiter has many moons, Saturn has many moons, Uranus has many moons, Neptune has many moons. If giant planets form elsewhere, why wouldn't moons form there as well? The logic is compelling. The challenge is detection. Finding exoplanets is already difficult. Finding moons around exoplanets is dramatically harder. Imagine trying to detect a firefly orbiting a lighthouse from thousands of kilometers away. The moon is smaller, dimmer, and often hidden within the signal of the planet itself. Nevertheless, astronomers continue searching. One of the most intriguing candidates is known as Kepler 1625 b.I. The name is not particularly poetic, admittedly. Astronomers are not always famous for elegant naming conventions. Still, the candidate generated enormous excitement. Observations suggested the possible presence of a moon orbiting the giant exoplanet Kepler 1625b. If confirmed, the moon would be enormous, potentially comparable in size to Neptune. That alone would make it unlike anything in our solar system. Imagine a moon approaching planetary dimensions. The discovery would dramatically expand our understanding of what moon systems can look like. At present, the evidence remains debated. Some researchers consider the candidate promising, others urge caution. More observations are needed. Science often progresses this way. Interesting hints arrive first, confirmation comes later, or sometimes doesn't come at all. Yet even the possibility is important, because it demonstrates that exomoon detection is becoming increasingly realistic. A few decades ago, astronomers were still debating whether planets around other stars existed in significant numbers. Today they are searching for moons around those planets. The pace of discovery has been extraordinary. Another fascinating possibility involves habitable exomoons. For years, discussions about extraterrestrial life focused primarily on planets. Understandably so. Earth is a planet. Looking for Earth-like planets seemed logical. Then scientists started thinking more carefully about moons. After all, some moons in our own solar system may contain oceans, some possess atmospheres, some experience tidal heating, some have complex chemistry. Why should exomoons be any different? Imagine a giant planet orbiting within the habitable zone of a distant star. Now imagine a large moon orbiting that planet. The moon receives energy from the star, additional energy from tidal heating, perhaps reflected light from the planet, perhaps magnetic interactions as well. Such a world could potentially maintain conditions favourable to liquid water, perhaps even life. Again, we should be cautious. No habitable exomoon has been discovered, no extraterrestrial life has been detected. The evidence simply isn't there yet. But the scientific reasoning is sound. If nature produces moons elsewhere the way it does here, some exomoons may be remarkably interesting places. In fact, some researchers suspect large habitable moons could eventually prove more common than Earth-like planets. That's a profound possibility. For centuries, when humans imagined life beyond Earth, they imagined other planets. Perhaps the future will force us to think differently. Perhaps some of the galaxy's most interesting environments orbit planets rather than stars directly. Perhaps moons are more important than we realized. Theoretical studies have explored a wide range of possibilities. Some exomoons might resemble Titan, others might resemble Europa. Some could be larger than Mars. A few might rival Earth itself. Their skies could be spectacular. Imagine standing on a moon orbiting a giant gas planet several times larger than Jupiter. The planet would dominate the heavens. Its cloud bands might stretch across huge portions of the sky. Ring systems could create breathtaking views. Eclipses might occur frequently. The visual experience would be unlike anything on Earth. And yet, despite the exotic scenery, the underlying principles remain familiar. Gravity, orbital motion, planet formation. The same processes that created moons in our solar system likely operate throughout the galaxy. That's one of the most powerful lessons astronomy repeatedly teaches. The solar system is not unique. It is one example, a useful example, a nearby example, but not the only one. The categories we've explored throughout this journey probably extend far beyond our local neighbourhood. Regular moons, captured moons, volcanic moons, ocean moons, atmospheric moons, giant moons, double worlds. Exomoons may contain all of them, perhaps stranger varieties as well. The universe has had billions of years to experiment. It would be surprising if it stopped with the examples we already know. What makes rogue moons and exomoons especially fascinating is that they represent the frontier of moon science. For most of human history, moons meant the moon. Then telescopes revealed Jupiter's moons. Then spacecraft revealed entire populations of extraordinary worlds. Now the search extends beyond the solar system itself. We're moving from exploration to census-taking, from discovering moons to understanding how common they truly are. After examining every major moon type we know, from cratered relics and volcanic worlds to hidden oceans, atmospheric moons, giant companions, double worlds, rogue wanderers, and distant exomoons, what do all these remarkable objects collectively tell us about the universe itself? When most people hear the word moon, they think of one object, the moon, the familiar companion of Earth, the bright disk that rises above cities, deserts, forests, oceans, and mountains, the object that has accompanied humanity throughout recorded history. At the beginning of our story, that seemed like a reasonable place to start. Yet after exploring regular moons, captured moons, irregular moons, shepherd moons, chaotic moons, volcanic moons, ice moons, ocean moons, atmospheric moons, cratered moons, dwarf planet moons, giant moons, double worlds, rogue moons, and exomoons, the word moon no longer feels nearly so simple. In fact, one of the most remarkable lessons astronomy has taught us is that moons are not a single category of world. They are an entire population of worlds, a vast collection of environments shaped by different histories, different materials, different sources of energy, and different relationships with the objects they orbit. Some moons resemble planets, some barely resemble moons at all. Some challenge our definitions, some challenge our expectations, and together they reveal something profound about the universe. The universe likes variety, far more variety than human beings originally imagined. If we could travel backward in time a few centuries and tell early astronomers what we've learned, many of the discoveries would sound unbelievable. A moon with active volcanoes more powerful than anything on Earth. A moon with rivers and lakes. A moon with a dense atmosphere. A moon hiding an ocean beneath ice. A moon larger than Mercury. A moon that tumbles chaotically through space. A moon orbiting a dwarf planet so closely matched in size that the two worlds behave like partners. The list would sound less like astronomy and more like fiction. Yet every example is real. Every example exists because gravity and time have spent billions of years experimenting. That's one of the most important ideas to take away from moon science. Nature does not build worlds according to a single blueprint. It builds them according to opportunity. Give gravity enough material and enough time, and astonishing things emerge. Sometimes the result is a planet. Sometimes the result is a moon. And sometimes the distinction between the two becomes surprisingly difficult to identify. Consider Ganymede, the largest moon in the solar system, larger than Mercury, possessing a magnetic field, containing enormous quantities of water. If it orbited the Sun directly, most people would call it a planet without hesitation. Yet because it circles Jupiter, we classify it as a moon. The same is true for Titan. Titan has weather, clouds, rain, rivers, lakes, a dense atmosphere. In many ways, Titan behaves more like a planet than some objects officially classified as planets. Again, the distinction comes down largely to orbital relationships. These examples remind us that categories are useful tools, but nature does not necessarily organize itself according to human preferences. The universe is under no obligation to keep things tidy, and moons repeatedly demonstrate that fact. They also reveal another important lesson: location matters. The same basic ingredients can produce dramatically different outcomes depending on where a world forms and what influences it experiences afterward. Io and Europa both orbit Jupiter, both formed within the same broad system, yet one became the most volcanically active world known. The other developed a hidden ocean beneath ice. Titan and Enceladus both orbit Saturn. One possesses a thick atmosphere and methane weather. The other ejects enormous plumes from a subsurface ocean. Even neighbouring worlds can evolve in radically different directions. This pattern appears everywhere we look. Small differences accumulate. Gravity reshapes orbits. Heat alters interiors. Collisions redirect histories. Over billions of years, worlds diverge. The result is diversity, an extraordinary diversity, and perhaps nowhere is that diversity more obvious than in the search for potentially habitable environments. For much of scientific history, the search for life beyond Earth focused primarily on planets. That approach made sense. Earth is a planet. If life emerged here, perhaps similar planets elsewhere would host life too. A reasonable hypothesis. Then moon science complicated everything. Europa appeared, then Enceladus, then evidence for subsurface oceans on other worlds. Suddenly, researchers realized that habitable environments might exist in places nobody had expected, far beyond the traditional habitable zone, far from the warmth of the sun, protected beneath thick shells of ice, powered by gravity rather than sunlight. That realization was revolutionary. It expanded the number of potentially interesting environments throughout the universe. Instead of asking only whether planets might host life, scientists began asking whether moons could as well. The question remains unanswered. No extraterrestrial life has been discovered. Not on Europa, not on Enceladus, not anywhere else. But the possibility is now taken seriously, and that alone represents a major shift in perspective. Moons have forced us to think more broadly about what kinds of worlds deserve attention. Another lesson emerges when we examine captured moons and irregular moons. The solar system was not always the orderly place it appears today. Modern planetary systems can seem stable, predictable. The planets follow their orbits, the moons follow theirs. Everything appears permanent. Yet the evidence preserved by captured moons tells a different story. Triton likely originated elsewhere. Phoebe likely originated elsewhere. Countless irregular moons probably began in entirely different regions before being captured. These worlds preserve evidence of migration, encounters, and gravitational disruptions. They reveal a solar system that was once dynamic and chaotic. Worlds moved, objects collided, moons changed owners, entire systems evolved. The calm arrangement we observe today emerged from billions of years of change. In that sense, moons are historians. They preserve records of events that occurred long before Earth became habitable, long before dinosaurs, long before oceans, long before life itself. Every crater, every orbit, every unusual characteristic tells part of the story. And because many moons preserve ancient features that planets often erase, they become invaluable archives. Without them, reconstructing solar system history would be far more difficult. There is another reason moons matter. They teach humility. Again and again, scientists approach these worlds with expectations. Again and again, the moon surprised them. Before Voyager visited Jupiter, nobody expected Io to be erupting with volcanoes. Before Galileo studied Europa, nobody expected a hidden ocean. Before Cassini arrived at Saturn, few anticipated Enceladus would become one of the most important astrobiological targets in the solar system. Before New Horizons visited Pluto, many expected a relatively simple frozen world. Instead, they found astonishing complexity. The pattern repeats throughout planetary science. Every time we think we understand the limits of possibility, nature quietly expands them. Moons have been particularly effective at delivering those lessons, perhaps because they were underestimated for so long. For generations, they were viewed primarily as companions, secondary objects, interesting but not central. Today, that perspective has changed. Many moons are now considered destinations in their own right, worlds worthy of exploration, worlds capable of teaching us about geology, chemistry, climate, planetary formation, and perhaps even biology. In some cases, they may be among the most scientifically valuable places in the entire solar system. The future of moon exploration is likely to be extraordinary. New missions continue to target Europa. Future spacecraft will investigate Titan. Researchers continue developing concepts for exploring Enceladus. Interest in ocean worlds grows every year, and beyond our solar system, the search for exomoons continues. Eventually, astronomers may confirm large populations of moons orbiting distant planets. Some may resemble worlds we already know. Others may be entirely unfamiliar. The first confirmed habitable exomoon, if such an object exists, would rank among the most significant discoveries in scientific history. Imagine learning that a moon orbiting a distant planet hosts conditions suitable for life. The implications would be enormous. Yet even without such discoveries, moons have already transformed our understanding of the universe. They've shown us that interesting worlds are not confined to planets. They've shown us that habitability can emerge in unexpected places. They've shown us that geological activity can persist far from stars. They've shown us that diversity is one of nature's defining characteristics. Most importantly, they've shown us that the universe is far more creative than our first assumptions usually allow, and perhaps that's the perfect note on which to end. Because if there is one theme connecting every moon we've encountered tonight, from tiny shepherd moons guiding ring particles to giant worlds larger than Mercury, from hidden oceans beneath ice to lonely wanderers drifting between stars, it's that every time we look more carefully, we discover something richer than we expected. A moon becomes a world becomes a mystery becomes a new question. And somewhere beyond the next question, waiting patiently in the darkness, there is almost certainly another kind of moon we haven't discovered yet,